So we're going to go ahead and get started here. And first up, we have John Spencer, and he's going to be telling us about the geology of Pluto and Charon, speaking on behalf of the team.
Yes.
So,
okay,
go ahead.
Thank you, Kelsey. Alan's a hard act to follow, but I'll do my best. I'm going to give a little bit more detail on some of the geology we've learned. This first picture, incidentally, is a new one that just came down a few days ago, just showing how we're still getting goodies from the spacecraft. I'm glad I'm giving this talk this year and not last year. We've come a long way. Let's see, I'm not getting my remote working. How did I switch off? Is there a backup remote? This one seems to have, the battery's died or something. Oh, it's working now. Okay. So New Horizons imaged the whole illuminated surface of Pluto at better than 20 kilometers per pixel. Thank you. You can see from this global view that there's broad latitudinal banding on Pluto, a bland at this resolution, northern hemisphere, the dark terrain in the center, but then we have this singular feature, which we were lucky to, it was on the, it wasn't totally luck, but we arranged for it to be on the hemisphere that we flew by at closest approach, that is Sputnik Planum, and a reminder that you'll hear a lot of, that these names that we're using are all informal at the moment. And this is really our best view of the close encounter hemisphere, the Charon-facing hemisphere. It's very intriguing, but it's difficult to say a whole lot about the geology in detail on this hemisphere. This is the part of Pluto that we imaged at high resolution during the close approach period. We have pretty much this whole hemisphere imaged at about 450 meters per pixel. And some regions at resolutions down to 80 meters per pixel. And I should say that the DEMs that I'll be showing here and the stereo have nearly all been done by Paul Schenk, and Paul Schenk and Russ Baer have done the base maps, and they will both be giving talks based on that later in the week. This is one of Paul's DEMs of the encounter hemisphere, or most of the encounter hemisphere. Sputnik Planum, of course, very obvious in the center here. But what I'm showing here is that the regions away from Sputnik Planum have a great deal of diversity as well. You'll notice the western side here is pretty uniform elevation. It's unmantled, but the eastern and northern regions are extremely topographically complicated. There are many layers of mantling there. This is a close-up view of some of that mantled terrain in the northern hemisphere, and this is, above this red line, is about where the mantling is prominent. We have moderate but still significant crater density in this region. It's mostly moderately old, but there's extensive erosion of the surface, as you can see from this image. If you look at the style of erosion here, and we move to another area that's a little bit over to the east, you'll see a very different style of erosion here, where we have very smooth, lobate scarps covering the area. These scarps are up to 4 kilometers thick, so whatever this mantling material is kilometers thick, and it's hard to know what's eroding it, but if it's just sublimation, that seems plausible, but it can't be sublimation of nitrogen, or at least not pure nitrogen, because the pure nitrogen could not support 4-kilometer high scarps, as we're seeing here in the, why am I having trouble with these? Okay, all right. So Jeff Moore will be talking more about that on Wednesday. It's quite mysterious what this material is, that it can hold topography, but it is not, but it is also capable of subliming over long periods of time, unless there's some other erosional process that we haven't figured out yet. On the western part of the encounter hemisphere, we see a rather simpler terrain, these cratered plains, which don't have much in the way of mantling, fairly high crater density, and there's some extensional faulting. You can see some extensional faults cutting across here. But these intercrater plains are actually very complex on a small scale. You can see, if you're close to the screen, there's small knobs covering most of this hemisphere, and there are erosional scarps that Jeff Moore will also be talking about. You can see one of them cutting across the bottom here. So this is this region here, a pretty extensive region to the west of Sputnik Planum, and this is a close-up of this region here. Cthulhu Regio is the large dark area to the west of Sputnik Planum running along the equator. And it's actually, geologically, it's not really a unit at all. There's some very lightly cratered regions, some of the heaviest, well, the heaviestly cratered regions that we see on Pluto, and some other terrain types as well. So this dark material that we're seeing along the equator is some kind of superficial coating that is preferentially being deposited or accumulating on the equatorial regions. The tectonics of Pluto is relatively simple. We see these graben here, which are several kilometers deep, and this is a map from the science paper by Moore et al. That just came out last week and gives a lot more detail on a lot of the things I'm talking about, showing the pattern of the tectonics, and some of the features are radial to Sputnik Planum, but many of them are not. There's not an obvious pattern, but it's consistent with some modest global expansion. Sputnik Planum itself is in this huge basin. It's 3 or 4 kilometers deep, these digital elevation models, because they're produced with a push broom camera, we haven't got all the artifacts out of them yet, or Paul Schenk has not got all of them out yet. So this striping, of course, is not real here, but the very evident raised margins of Sputnik Planum you can see here. The next slide shows some of that in stereo. For those of you who have the glasses, you can see the very distinct scarp coming up from the very flat floor of Sputnik Planum here, and some of the extremely complex fretted, eroded topography up here towards the top of this image. So it's a big basin. It's quite plausibly an impact basin, a very ancient impact basin. You don't see anything here that looks like an impact, gives it away as an impact basin, but it's circular except in the southern part, and it's at least a reasonable assumption that Sputnik Planum was originally a basin that has somehow got filled up with a lot of nitrogen or something rich in nitrogen. Okay, that's it for the stereo for a little while. This is now, Alan showed part of this movie as well, but this is now a transect across the full width of Sputnik Planum, starting on the Crun macula, some of the dark terrain on the southern edge. There is a region here with a lot of pitting, some of which seems to follow flow lines. Then there's a bland region that's around here. And then towards the center of Sputnik Planum, we get into these cells, which look very much like convection cells, and that's what we think they probably are. They change in character as you head up towards the northern edge of the planum. The grooves separating them seem to become less prominent. And then here we are on the northern margin and into some of the chaotic mountains that Alan showed as well. But even up at the top here, we see these very distinct cell-like features which look an awful lot like convection cells. Here is a map by Oliver White, who will have a poster on this tomorrow afternoon, showing the preliminary geologic mapping of Sputnik Planum, and the black lines here outline these apparent convection cells across the surface. You'll notice that they tend to be larger in the center and smaller towards the edge, which would make sense if they were controlled by the depth of the nitrogen that we see here. And then a large part, this is also part of Sputnik Planum down in the south, but does not have the convection cells. There's a very sharp boundary to them, and this is the region where those complex chains of pits occur. Alan also showed this slide, but this is a slide where we've taken a higher phase and lower phase angle image and ratioed them to each other. So you're seeing a plot of forward scattering where brighter regions in this image are more forward scattering and therefore probably, I say rougher, this is a sign error, I mean smoother. Do it? Okay, yeah, forward scattering would be smoother. Anyway, when you do this ratio, you see the outlines of the cells short, but the centers of the cells show this complex interconnecting pattern that, again, looks very much like what you might expect for upwelling due to convection. We have no idea why convection upwelling would be producing the surface textures that we see, but it's carrying this very distinctive spatial pattern that it's hard to explain by anything other than this being a big field of convection cells. This is just a close-up view showing what are presumably the convergence zones between these cells, which have medial ridges on them, and in some places have collections of pits which have dark floors, and we're open to suggestions as to what that means. Bill McKinnon will be talking about this tomorrow afternoon. There is evidence for not just convective but advective motion of this material, this presumably nitrogen-rich, very soft fluid ice up towards the northern margins in particular. We see a lot of flow patterns. You see material flowing around, what appear to be nunataks sticking up through the ice there. And if you look at the topography in this region, the region where all these flow features are is actually a bit of a groove. There's a depression along the edge of Sputnik Planum here. And so if this is in steady state, which of course it might not be, but this is a very young surface, so it's plausible that it might be in steady state, that means you have to have some kind of sink here to maintain this groove here, and that's another mystery. Is the material somehow flowing into the subsurface and being recycled? It seems odd, but it kind of looks that way from these images and the topography. We do see very clear evidence of glaciation coming down from the highlands on the east side of Sputnik. This is from a paper by Bill McKinnon that's going to be coming out in Nature shortly. That you see, I don't know how well you can see them here, but there are streamlines coming down through the highlands material out onto Sputnik Planum here. And it appears that whatever this highland material is, maybe it's rich in water ice, some of that material is being broken off and rafted down into the plains, and then is being caught up in the convection. So where it's caught up in the convection, it appears to be buoyant and is getting trapped at the margins of the convection cells, and in particular at triple junctions between convection cells. So we seem to have a nice story here of material being entrained and floating on the top of this convecting surface. This is more evidence that we have active convection going on here. We have, along the western side of Sputnik Planum, these very dramatic chaos regions. This is called Alidrisi chaos here, and you can see it here up in the northwest part. Here, if you go back to the DEM, you can see these regions of chaos all the way along the western margin of Sputnik. And it's tempting to think that maybe there's some flow from east to west, and these are being rafted along and accumulating on this edge. But there are many other ways you might do this, but it's a very striking pattern, a very striking asymmetry to Sputnik Planum here. And because water ice has a density of 0.94, or maybe less if it's porous, probably somewhat less, and the solid nitrogen at Pluto temperatures has a density of about 1 gram per cubic centimeter, you can actually float water ice in nitrogen. And so it's plausible that these really are giant icebergs floating in the nitrogen. But if some of the tallest ones here are up to 5 kilometers high. So that becomes a bit of a challenge to explain these as actually floating. unless they're very buoyant. But we haven't got a better explanation for now as to how these things are getting broken up and transported the way they clearly are. This is another stereo view if you want to put your glasses on again, just to show the very dramatic topography here. And this one here is 4 or 5 kilometers high above the edge of Sputnik Planum. Notice this little lake back here, which is clearly the same material as in Sputnik Planum. But this whole region is depressed relative to Sputnik Planum again. So this is not at the same elevation as that. Another mystery. We have lots of other very peculiar stuff. We have sublimation. Well, we say sublimation textures. We don't really know, but it's the best explanation we have. And Jeff Moore will be talking about that again. These bladed terrains on the tops of these mesas, they look a little bit like penitentes or sun cups on an enormous scale, on a kilometer scale. We have something that looks more like a cryovolcano than anything else plausible we can think of. This is Right Mons. It's 3 or 4 kilometers high, has a central depression 3 or 4 kilometers deep, a very complex but somewhat concentric texture around it, as though there's maybe cryoclastic material that is being deposited out of this depression and mantling around it and building up the surface. Kelsey Singer will be talking about this in a poster tomorrow. And then we have a lot of evidence for erosion of the surface on a finer scale. This is a figure from the Moore et al. Paper that just came out, just showing some of the variety, the amazing variety of erosional features that we see on Pluto, several of which look somewhat dendritic. We get fluting of slopes in this region here, remarkable converging patterns cutting into this escarpment here of channels. Great variety here, and we don't know what the fluid is here. It seems most likely that this is glacial erosion, or maybe it's subglacial. You can even imagine possibly liquid nitrogen below the surface, if you had enough nitrogen on the surface here. But that means if these are glacial features, those glaciers have gone, and we've had large variations in the distribution of nitrogen over the course of Pluto's history. And Alan Howard, or actually Urken, will be giving Alan Howard's talk on Wednesday about this. Cratering, this is a map by Stuart Robbins of the distribution of all the known in green and tentative in red craters that we see on Pluto. You notice the dramatic lack of craters in Sputnik Planum or its immediate surroundings. These are crater counts that Kelsey Singer will be talking about tomorrow. There are regions of Cthulhu, which I mentioned was a lot of cratered plains, and the region to the north have enough crater density that if you assume a model for the impact rate on Pluto from Greenstreet et al. 2015 based on the known population of KBOs and extrapolations from that population, then you get ages of around 4 gigayears for this material. So parts of Pluto are very ancient. But there are regions here east of Tombo, not just the surface of Sputnik Planum, where ages are more like 1 gigayear, and the cryovolcanic constructs are maybe of that kind of age as well. And then, because we see no craters at all on Sputnik Planum, the likely age is probably 10 million years or less. And Bill McKinnon has been working on convective timescales, and that's consistent with what you might expect for an actively convecting surface powered by the geothermal heat from Pluto. This is just gratuitous scenery, which I'm sure you've seen before, but I'll now say a little bit about Charon. This is a single image showing the correct relative distance and proportions of Pluto and Charon. Charon's about half the size of Pluto, about 1,200 kilometers across. Very interesting in its own right. Here's our best color view of Charon. And you can see 2 obvious physiographic provinces here. There's smooth plains that we're calling Vulcan Planum here towards the south. And then in the north, we have this terrain that's a little harder to see the topography because of the high sun angle, but it's clearly very rugged. It appears to be older because it's embayed by the smooth plains here. There are some large basins. This is Dorothy Gale up here. But there's not much correlation of albedo and geology. We see the dark stain here that Will Grundy may talk about later. That is apparently a surficial feature. But otherwise, the albedos are very similar between these terrains, and maybe there's some kind of surficial deposit that's painting everything the same color. The northern terrain is quite dramatic, and this is worth getting out those glasses again for. You'll see, even though you don't see the topography from shading very much, you see a network of very deep canyons here, which are shown in the DEM on the right here. They break up that highland terrain. We shouldn't really call it highland because you see there's not a dramatic difference in height, but there's a dramatic difference in roughness with the smooth plains. They break it up into polygonal blocks. Some of these troughs are 10 kilometers deep. Very dramatic topography. Ross Bayer will be talking about this on Friday, and Amanda Zangari has actually been looking at some of the stellar occultation data for Charon to see if we can actually see some of these troughs in the stellar occultation data that we've got over the last couple of decades. This shows a rim around Mordor Macula, the dark northern region here, but it doesn't look like an obvious impact basin, but at least in this part there's a distinct ridge surrounding it. And here is a 10-kilometer deep trough, which shows up very obviously in the stereo. And so you can see just this extremely rugged, heavily faulted terrain here. Here's Vulcan Planum in our highest resolution overall view of it. Also a very complex surface, but very smooth on a large scale. This is our highest resolution view of Vulcan Planum with lots of fine textures, pits over here and linear features here. We've been doing geological maps. So this is a map by Stuart Robbins. You'll notice we think there's an extension of Vulcan Planum out here into the rugged northern terrain. And there's a lot of evidence for viscous flow in Vulcan Planum. The edge of the smooth plains has a bit of a moat around it, and then, which you can see in blue here. And then several mountains here towards the terminator also have moats, so as though you've had a viscous material that hasn't quite made it to make a flat surface against those mountains. And then here's some really striking stuff that looks more like viscous flow than anything else we can think of. You can fit simple flow models to get an estimate of viscosities, and they come out about 10 to the 14 Pascal seconds near the time of freezing. Similar to what has been seen on Ariel here by Jankowski and Squires from the Voyager data back in the 80s. And so this is consistent with at Charon temperatures with probably some volatile rich ice, maybe an ammonia ice mixture could give you these kind of viscosities. I'm having more. It's not changing. I must be doing something wrong, but okay, here we go. All right. The cratering record of Charon is consistent with ages around 4 gigayears, so we don't see very young terrains on Charon. One of the most interesting things is that we think we can rule out some of the models for the Kuiper Belt populations of small bodies, which have very large numbers of small objects, because we just don't see the large number of small craters as you would expect if there were that large a number of kilometer scale objects. And I will try and finish up here. Okay, so conclusions for Charon. We see impact cratering, we see massive extensional tectonics, probable extrusive cryovolcanism, probably some kind of superficial coating to give the uniform color, but everything is about 4 gigayears old. For Pluto, we see much greater variety of surfaces, processes, of course, impact cratering, some limited extensional tectonics, buoyancy-driven mountain building, best we can tell, glacial flow and erosion, convection and advection of nitrogen ice, sublimation, some things producing all those mantles. We have no idea what that depositional process might be. Probable cryovolcanism, and ages all the way from 4 gigayears until only less than 10 million years. So a very dramatic and very varied system, and it's going to be keeping us busy for a long time. Thank you.
All right, time for some questions. It's hard to see.
John?
Here.
Hi, Bill.
I just want to make a tiny technical correction. The paper on Sputnik Planet is under review.
Okay.
Okay. It's
I jumped the gun on that. That is Bill.
I appreciate the,
that is Bill's
your
paper.
kind wishes, but fate lies with the reviewers and the editor.
Thank you, Bill. And that is Bill's paper, of course, so he would know.
You don't have a
Anybody else
microphone
out
yet,
there? Yes.
You don't have a microphone yet. do you?
Jennifer Anderson, Winona State University.
Okay. Oh,
I'm
never
wondering,
mind.
do you have any energy source for what's powering the convection? Is it just, do you have any
We
ideas?
think it's possible to do it with the geothermal heat that you expect from radionuclides within Pluto. If it was water ice, you couldn't do any of this. But given that we have this much lower viscosity, probably nitrogen-dominated ice, it's a lot easier to do this kind of thing. So that's probably what's going on there.
All right.
All right.
Well, that's good because we need to move on. So thank you, John. And next up is Will Grundy. He's going to be giving a summary of the composition of Pluto and Charon.
And
They're going to bring
okay,
you a clicker, hopefully.
and my slides would be good too.
Do we need some more 3D glasses out there? Raise your hand if you don't have
I don't have
one.
any 3D stuff in here, I'm afraid.
Oh, never mind. Next time, next round.
So,
Okay, you're
all
good.
right, so we're live.
I think so.
All right, so this is work that's very much still in progress by a large, hardworking team. And I'll definitely not give them the credit they deserve just because I'll be pressed for time, but there's the names there. What I'm going to tell you about is coming by and large from this one instrument, Ralph, which is actually really two instruments. It's a color camera and a infrared imaging spectrometer that share one small telescope by means of a dichroic beam splitter. And there you can see it being worked on in the lab and where it's mounted on the spacecraft. So the color camera consists of 7 CCD arrays, of which 4 of them have color filters just pasted right on top. And the way you work this is time delay integration. So you scan the field of view across the scene that you're trying to capture, and you track the charges off of these very tall, skinny CCD frames at the correct pace to not smear it, if you're lucky. And the dimensions of these arrays are 5,000 pixels in the long axis and only 32 or 64 pixels or whatever in the sideways axis. But as you can imagine, you can just sweep this across the scene as long as you like, and you slurp up a lot of pixels fast. So you can make very large scenes with this thing, and that's part of why it's been taking a long time to get the data home, because it captures a lot of pixels. The infrared spectrometer works similarly in scanning fashion, where it's a 256 by 256 array with a wedge filter basically pasted right on top. So each column in the array is a wavelength. And if you sweep that across the scene, you will have eventually seen each piece of the scene at each wavelength, and you can stitch it back together again. As you can see, we don't have reaction wheels. We're in a dead band with hydrazine thrusters firing occasionally to stay in the dead band. Every time the thrusters fire, the motion changes, as you can sort of imagine from this cartoon. This is not real data, just a cartoon, but stitching that all back together again is non-trivial, especially because the axes aren't perfectly orthogonal, so the rate of scan also changes each time a thruster fires. The USGS's ISIS software is doing a pretty nice job of that, and I imagine with a little bit more fine-tuning it'll be even better, but that's what we're using to reconstruct image cubes from this. The wavelengths is 1.25 to 2.5 microns, which is a very convenient wavelength range for icy materials because a lot of them have infrared vibrational features in that wavelength range. Okay, Alan already showed you this picture, and it's, you can buy t-shirts with this stuff on it. It's out there. This is the only natural color picture that I'll show you because the wavelength that the human eye is sensitive to isn't actually a particularly useful wavelength for remote sensing ices. It basically all looks like different shades of brown sugar. If you take advantage of the filters that we have, you can do what we're calling enhanced color, where you just simply put the shortest wavelength filter into the blue channel and the longest wavelength filter, which is near infrared, into the red channel, and the red channel, which is actually red, you put that into the green channel, and so they're in order of wavelength. And then you can see that there's a lot more going on in terms of, I should use a pointer, except that I can only point at one at a time. So, okay, so over here you can see that there are strong latitude effects where the equator is this darkish material, and you can see a lot of color contrasts that are different at mid-high latitudes and lower latitudes. I'll talk more about that in a bit. You can also take the wavelengths that are the MVIC filters, and you can pull out some extracted parameters. And this one is a spectral slope and the amount of absorption that's in the methane filter, which was this last filter down here, which is sensitive to a fairly weak band in methane ice. And so anywhere that you see a strong absorption there, it shows up blue in this particular image. That's where you have really large grain sizes or very high concentrations of methane. I could dwell on this and zoom in on this and have a lot of fun with it, but I want to move on to the infrared stuff, which is even more higher information content, albeit lower spatial resolution. So this is just a false color image of the encounter hemisphere of Pluto in 3 arbitrary near-infrared bands. And you can see there's artifacts, and you can see there's a lot of warts and all, but only point I'm really trying to make with this is that there's a huge amount of spectral diversity in the near-infrared spectra, and I've just pulled spectra out of various different interesting spots on Pluto, and you can see it goes from almost flat, not super low albedo in Cthulhu, to much higher albedos up near the pole with very strong methane absorptions. This green spectrum has a really strong nitrogen ice absorption feature right there, which I think corresponds to that pond, the frozen over pond that John showed. So it's actually even stronger than in Sputnik, and so on. So what do you do when you're confronted with, especially if you're a telescope observer like me, who counts himself lucky if I get a few spectra a year? What do you do when you're confronted with 100,000 spectra? You got to change your game. And so we ran around the composition team and said, what would you do if you were confronted with 100,000 spectra? And of course, it's the things that you guys have been doing in the Mars community for years and years and years, but everybody had a different approach to it, which was great because it meant that, that we could compare and contrast the results that we were getting. So my approach was the quick and dirty thing, which was to just make an integrated band maps that were targeted at specific species. So this was the CH4 ice band map. This one was nitrogen ice. And those are in the science paper that came out last week. We showed these at DPS, so these aren't that new. Some of the other techniques have taken more time, but are probably more valuable in the long run. Bernard Schmidt and Sylvain Philippe have been working on improving the index maps by, well, for starters, doing principal component analysis to eliminate a lot of the noise in the spectra, and then reconstruct the cube without the very high order noise components, and also cook up different indices that seem to be more diagnostic. And you can see this is the generation of nitrogen maps beyond the one that I made. The one that I made was this, and it's really pretty crappy. And so these are 3 successive generations that Bernard and Sylvain have made, and they're gradually revealing more and more details in the surface, and definitely see their talks in the next 2 days. Jason Cook has been pulling out regions of interest so that he can beat down the noise a little bit by averaging a few spectra together, and then doing Hapke modeling of those. And he's got some very cool results on the non-volatiles in Cthulhu that he's going to show soon. Silvia Protopapa has been actually brute force doing HAPI models of every single pixel in the scene using a supercomputer. And in order to do this in any kind of reasonable amount of time, you have to cheat a little bit and simplify the models and only have a small number of free parameters. But it's probably the most quantitative way of making a composition map, assuming that we get the right free parameters in there. And so these are examples of stuff that she'll be talking about, where she's talking about two phases: the nitrogen-dominated phase with methane dissolved in it at its saturation limit, and the methane-dominated phase with nitrogen dissolved in it at its saturation limit. And their distributions are somewhat different spatially. And Christina Dallory has been doing clustering techniques. This is actually a Charon cube, not a Pluto cube. Just starting to see subtle variations across the surface of Charon in terms of the depths and shapes of the water ice bands and slopes and things like that, although the variations are quite subtle, as she'll talk about. All right, so what I want to do is not dwell on the details of the data. I want to talk more about what the patterns are that we see in the data. So this is, starting at the left, is a completely non-volatile material at Pluto's surface temperatures of 40, 50 Kelvin, water ice. That's bedrock. And at the right is nitrogen ice, which is very, very mobile at those temperatures. And in between is methane, which is about 3 orders of magnitude lower vapor pressure than nitrogen. So it's in between, although it is definitely volatile. I neglected to put a lat-long grid on here, but basically the equator is sort of a smile across the bottom. And if you march from the equator to the pole, you go from no volatile ices. Then you start to see methane, which is the least volatile ice. And then you get to an area which is rich in nitrogen. And then the nitrogen fades back out, and you have lots of methane up at the pole. And this is, remember, this is the summer pole. So this is being cooked in continuous sunlight for the last few decades. So that's one pattern that we see. But there's also topographic effects. And this is a good illustration of it, where this is one of these mountain ridges that's in the eastern part of Cthulhu Regio. We're going to have to come up with a name for this mountain ridge, because we keep talking about it. This is a methane map, and you can see that the methane corresponds very nicely to the peaks of the mountain ridge, where it's also painted white. So that white stuff is methane ice, or it's certainly very rich in methane ice. Another pattern, though, that you can also see here, which we haven't really called attention to so much, is if you look at several of these craters up here near the top, and this slope here, it's the north-facing slopes in this particular region that also have methane ice. So there's an orientation effect as well, somehow or other, with the interaction with the sunlight, that's also dictating where methane ice is comfortable. And if you go to other latitudes, you'll find different patterns comparable to this, but little regional patterns. And then the last pattern, I want to just come back to these maps for it, is I didn't talk about Sputnik Planum, which is this huge interruption to this simple latitude-dependent pattern that I've been talking about. That's a deep basin, as John mentioned, and it's got all of the volatile ices in it. I didn't show the CO map because it looks really crappy, but it looks a lot like the nitrogen map. So Sputnik Planum is got all of the volatile ices, despite being near the equator. That's presumably because it's a topographic low. But if you look just to the east, the eastern part of the heart, Tombo Regio, you'll notice that it also doesn't really follow the latitude pattern. And I think that's an example of a regional effect, where somehow or other the existence of Sputnik Planum here is causing material to be deposited to its east that wouldn't otherwise get there. Presumably prevailing winds are coming from the west and blowing stuff towards the east, whether it's erupted out of fissures or whether it's sublimated away, I have no idea, or if it's dust that's mobilized off of the surface. But it's quite methane rich here in the east, and that strange snakeskin bladed terrain is this stuff here, Tartarus dorsa, is very, very methane rich. Now, is methane structurally strong enough to build that stuff? I don't know. Or is it acting as a cement and gluing together water ice particles, or who knows? But that's an example of yet another kind of compositional difference as you move across the surface. All right, so I do want to also talk about Charon a little bit. And both Alan and John have alluded to this reddish area, which more or less corresponds to Mordor Macula, which is the darkest reddish area, and there's a bit of a ridge around it. But it continues outside of there and is well aligned with the pole. This is Lisa, again, it's just taking 3 random wavelengths and putting them into the colors just to make a Lisa color image, false color image. But pulling out spectra of the pole and basically anywhere else you want to pull out a spectrum, they all look very, very similar to one another, being completely dominated by these water ice absorption bands, including up at the pole. So where all that red stuff is not preventing you from seeing water ice. Now there is a bit of a slope difference up at the one spectrum in the pole, where it is a little bit redder at the shortest wavelength end. So that's probably the signature of that red stuff, but it doesn't have any other obvious absorption bands or anything like that to distinguish it from the rest of the surface. And you can see by the modeling of the color that there are subtle spectral variations across Charon as well, but we haven't really figured them out yet. Another one that's well worth pointing out, though, is this little spot here has a dip at about 2.2 microns, which is one of the 2 bands in this wavelength region for ammoniated species, the other being right at 2 microns, which is a little hard to see because there's a strong water ice band there, but you can see it also has that one. Let's see, I can't remember what my next slide is. Yeah, okay, well, that's a good one to have there. Somebody should have thought of that. So this is a zoom of this little region, and I guess I did a little bit better job of picking out the region of interest here because it's a little sharper down there. There's 2 craters in that region that are about the same size, roughly 5 kilometers across, with bright ejecta rays. They're also surrounded by maybe a little bit of darker material further out in both cases. And if you map this ammonia band, it shows up really strongly there, and it doesn't show up at all here. So what's up with that? It's certainly true that ammonia is destroyed by space radiation, at least in the optically active millimeter or whatever that we're looking into here. So it's possible that this is a crater that's less than 10 million years old. Kelsey could probably tell me what the odds of that are. We see one, so actually there's a couple others that might have it, but this is the best example by far. I think if this one was 100 million years old and this one was 10 million years old, would they both look similarly young? I don't know. It's a bit of a puzzle. But ammonia is an ingredient that we've been claiming must be on icy satellites forever and ever and ever, and we've never had a really nice spectral detection of it, despite the fact that it's the best excuse for high viscosity eruptions on the surfaces, or one of the best excuses, and also for suppressing the melting points in the interiors. So geophysically, ammonia ought to be all over the place, but we finally see it. Colors on Charon, so this is getting actually back to the red pole, is a very simple pattern of colors. So this is just ratios to first order take out the photometric effects, and you basically see a mixing trend where most of Charon's surface is neutral, and there's a spray of redder stuff going off this direction. And I didn't really darken that or brighten that up enough to see it very well, so we might have to just sort of skip over this stuff. Here's Pluto by contrast, and you can see it's a very simple just mixing line for Charon, but for Pluto, there's multiple things going on in clumps, and this it has a curve to it, and there's a couple of little things going on down here. So Pluto's a lot more complicated color-wise, but Charon is quite simple. And you can see the same thing if you do the principal component analysis, where the first principal component, where you're not just sensitive to the shading across the scene, is responding to it actually is sort of like blueness, so it's anti-pole, but I could have turned that upside down if I'd wanted to, but that's just the way it came out. And here you can see quite well that the redness extends beyond that most concentrated region that we're calling mortar macula and actually covers a wider area. And you notice that by the time you get down to principal component 3 and 4, it's basically chasing noise. There's really, Charon's quite simple. It's gray water ice that's polluted in some way to make its albedo lower, and it's red stuff mixed in with it at varying amounts. Pluto, by contrast, has all kinds of energy in all of the principal components that it's too bad we didn't have more filters, because it would have had energy in those too, but you'll notice that this is the weights that are needed in each of those, and on Charon, all of the extra energy is basically in the first principal component other than the one that's just responding to the photometry. And there's very little weight in these, whereas on Pluto, they're sort of more spread out amongst them. All right, so the hypothesis that we pitched in the science paper is that gas escaping from Pluto or from Charon's interior that has methane in it will find its way to the winter pole, which gets extremely cold, and it cold traps there. This is just showing you where the redness is. So these are just binned in latitude bins, color ratio. This is just showing you that the winter pole, because of the high obliquity, gets no sun for decades and decades, so it gets cold. These are thermal models where the diurnal variation at any given latitude on here, which is color-coded. So for the equator, you get a large diurnal variation because you're always going through day-night cycles. At the poles, you spend decades getting very, very cold, and below about, 24, 20-something Kelvin, you would cold trap methane. And then once it's cold trapped, if you irradiate it and you break off a hydrogen, that escapes to space. And the CH3 radical that results from that is going to stick to whatever its neighbor is, which is probably another methane, and make something like ethane, for instance, that's not volatile when it comes back into the spring sunlight. And so it won't sublimate away. So anything that you can make that's heavier than methane is going to stay, and then it will, over a much longer time scale, be photolytically or radiolytically gradually converted into tholins. So that's the hypothesis that we're claiming, and I'm doing a bunch more modeling right now, but I will jump to my conclusions because I heard the beeper. In summary, there's a lot of compositional contrast as you go across Pluto's surface. It's really quite striking, and they're controlled by more than one kind of distribution. It's both seasonal latitude kinds of effects and also topographic local regional effects, and then also larger regional effects, which I don't think we're going to even begin to understand until people are doing global circulation models that have all of these volatiles in it. The volatiles interact in very complicated ways and get sorted, distilled, recombined on a whole bunch of different timescales. So there's a lot to learn. And the distributions that we've observed are valuable clues to those processes, and so people that are making models will have plenty to test against. And then again, Charon also manages to be unique among icy satellites, even though it's pretty typical in size, and we have quite a few icy satellites in the solar system that are in this general size range. Charon manages to throw a few surprises at us. Thank you.
Great. We definitely have time for questions. So let's just start over here on this side, front, left for me.
Adrian Brown, Sony Institute. Great talk, Will. Thanks for that amazing data. I'm struck by the regularity of your water ice spectra on Charon. Is there any evidence for smaller water ice grains, like smaller water ice absorptions? You showed some very homogeneous water ice spectra.
You're talking about variation?
Yeah, is there any variations in the...
It's surprisingly little variation, and in fact, I think Christina is going to talk about that, and Jason might talk about it a little bit in his talk as well. I will just note that Simon Porter did a paper a year ago where he pointed out that dust from the small satellites, some of it will find its way to Pluto, and so maybe there's a story there with, infalling water ice dust.
Yeah.
Right. And inside the team, what's the thought on the difference in abundance of water ice in Charon compared to Pluto?
Oh, I think they're both densities are not that different from one another, so the bulk abundance is similar in both. It's just that on Pluto, it's covered up by all this volatile stuff that moves around on seasonal timescales. And on Charon, if you put volatile ice on Charon's surface, it'll hop around a few times ballistically before it, works up to escape velocity. But, the probability of escape is non-trivial per hop.
We'll do the back, our right.
Ellen Sansom, Curtin University. The red spot on Charon, you're saying is from irradiated material from Pluto. Is that something that's ongoing, do you think? Because there is a large impact crater that appears to actually overprint that.
If it's going quite slowly. I think it is probably still going, but that large impact crater, if that is even an impact crater, it's not normal
I think
basin
she might be
shape.
talking about Dorothy Gale.
You're talking about the, okay, right. You're talking about,
Are you talking about this one?
Yes, yeah.
yeah, right. And that can't have been a recent development.
No.
Yeah, there's also a couple of smaller craters that are on top. Like this one interrupts the pattern, and these two little guys. So maybe it has tailed off. Maybe today's rate is slower than the rate was 4 billion years ago. But it's not so slow that it's completely obliterated. I mean, if you count the craters in an area this big down here, you're going to have a lot more of them than what you see punching through the red up there.
Yeah,
Thank you.
interesting timing question. Up here.
Hi, Sean O'Hara, University of Illinois, Chicago. The Vulcan planum seems to show evidence for viscous flow, which is at least suggestive of a compositional difference. The spectra you showed doesn't seem to have doesn't seem to show a lot of that difference. Would that be due to the radiolytic dissociation of the volatiles on the surface, or is there another reason for not seeing a big spectral difference there?
I thought that was going to be the very first thing. I mean, when I saw pictures that looked like this, I was like, oh boy, I'll just pull out a spectrum down here and a spectrum up there, and they're going to be different. And I was very disappointed. So how do you do that? I don't really know. These are ancient surfaces, and they've been heavily gardened and perhaps polluted externally, but that was a surprise to me.
We'll keep up here.
Hi, Chris Klein, Southwest Research. You mentioned that Sputnik Planum has all of the volatile ices, and people have discussed nitrogen glaciers and convection there. Has your team yet been able to constrain the proportions of the different ices?
Yeah, so that's where did I put the clicker? That's the work that Sylvia Protopapa was doing. Let me see if I can find her slide. Yeah, so in this particular model, it's the nitrogen-rich phase on the left and the methane-rich phase on the right, and those are quantitative numbers. That's the mixing fraction on the scale bar on the left. And there's other components in the model, too.
How would CO fit into this story?
Well, here's a bit of a problem. These things are all soluble in one another to varying degrees, and we have the binary phase diagram for nitrogen methane, but we don't have the ternary phase diagram. And if you can make it, I would be glad to get my hands on it. Otherwise, I'll have to do it myself. That'll take a while.
New project, Chris.
New project.
Go ahead.
Hi, Alex Trowbridge, Purdue University.
whatever.
I asked this question at DPS, but I was wondering if you had, with more data, you had a better answer. Do you see the alpha as well as the beta phase for nitrogen, or is it just beta?
We've never seen any sign of alpha.
Can you say something then on the concentration of carbon monoxide? Because at 10%, those two phases are both stable at Pluto's temperatures.
That's an excellent point. And if it was only carbon monoxide and nitrogen, I would go out on that limb with the binary phase diagram. But again, I don't know what the ternary phase diagram does.
Thank you.
Let's go to the back right.
Hi, my name is Heather Kaluna. I'm from HIGP at University of Hawaii. And I was just curious if you had any knowledge about the stability of the spin axis of Pluto and how that might play into this latitudinal variations.
Right. So there's an old paper by Dobrovolskis that was then Binzel and Earl took that and ran what the numbers would do over the last few million years. And the pole does precess within...
And plus 20 this way.
Yeah, plus or minus 20?
Yeah.
Or within a 20 band?
No, plus minus 20.
Plus minus 20, yeah. So it's a non-trivial variability. And it's been shown that you can't run that back more than tens of millions of years before it becomes chaotic, in the sense that you can't take today and run it backwards and get the right answer, because the noise blows up on you. But so yes, it varies, but within a range.
Yeah, there's some good stuff you can see on the climate cycles for other people on the team. And Bill's
One last
back.
question.
It's not even a question, just to amplify some of your comments, Will, both to Alex Trowbridge and to Glein's question. The nitrogen 2.16 absorption feature in beta nitrogen requires path lengths of centimeters, and so in order to see it, we're seeing a lot of nitrogen, so we know it's a nitrogen-dominated composition. We wouldn't even see alpha nitrogen if it was that cold, because it's so narrow.
Incidentally,
that's my judgment.
There's a poster that shows a new absorption band that only emerges when you have CO and nitrogen mixed at the molecular level that's downstairs.
Okay.
Great.
Okay,
Thanks,
thank you.
Will.
Thank you, Will.
All right. Now we're going to have Mike Summers representing the atmospheres team, and the title is The Neutral Atmospheres of Pluto and Charon.
Okay, thank you. In the spirit of full disclosure, this is about the atmosphere, not the surface or the interior. So I won't be too offended if you go to another session. So anyhow, I'm going to talk about the atmosphere, sort of where we stand in terms of understanding it. I do want to acknowledge some people that have helped a lot with this talk. Certainly Randy Gladstone, who is the theme team lead for atmospheres. Randy and I have known each other for 31 years, and since graduate school, we spent 2 years together in an office, and we've started arguing about Pluto then, and we still are. I guess we have a pretty good compatibility index, but I certainly want to acknowledge him, and of course Alan, who led us to Pluto. And these are the people that have provided slides for this talk. I'm not going to go through all of them. I do want to say that most of the people on this team have spent a large fraction of their career, sometimes their lives, thinking about Pluto. So you would expect that we would have a pretty good idea of what we were going to see when we got there. That wasn't true even slightly. I've given about 20 talks since the encounter, and I've tried, just for my own benefit, to quantify two things. One is the degree of surprise that I had personally at the things we saw, and early on I was giving numbers like 70% of the things we saw I was surprised about. Now I'm probably up around 95% of the things we see. We were surprised about the atmosphere. Not everything, but just about everything. In terms of understanding what we see, early on I was saying, well, we probably understand 60 or 70% of what we're seeing. Now I'm down to around 20, 30%, something like that. So we've had to retool a lot of models. We've had to think about things in new ways, come up with new ideas. And I'm not going to talk about the models or the details of the observations, just give you a few things that tell you where we are in terms of what we saw and what we're trying to understand. So the way I'm going to do this is start talking about the radio occultation experiment first, which gave us the lower atmosphere and temperature profiles. Then I'm going to talk about the ALICE solar occultation experiment, and it gave us a lot of information on the middle and upper atmosphere. And then go into hazes, and then say a little bit about Charon occultation. So, as this works, okay. So, and as I go through, I'm going to also try to summarize where we stand with each of these things. The radio occultation experiment is perhaps the easiest. This experiment essentially measured the phase delay of radio signals penetrating the atmosphere, transmitting through the atmosphere of Pluto at 2 points. The entry and the exit occultation that's shown on this geometry. So almost opposite sides of Pluto. From the phase delays, we can get temperature and pressure and their profiles in the lower atmosphere. The figure in the upper left, you might think that it looks pretty good, and maybe the temperatures from entry and exit do sort of asymptote to about the same numbers, maybe 110 degrees, something like that. But the lower part of the atmosphere here is very, very interesting, and two completely different things that we see on the different sides of Pluto. The entry occultation shows clearly that there is a temperature boundary layer of some sort, not a troposphere, but a boundary layer. And that's close to Sputnik Planum, so that may be an interesting relationship there. The exit showed a continuous monotonic increase in temperature with altitude, which is, that was one of the models that we kind of were considering before we got to Pluto. But that one's a little bit off as well if you look at the details. One interesting thing is that the surface pressure from both places is fairly comparable. The entry pressure is 11 microbars and the exit pressure 10 microbars. Okay, it sounds pretty close. 10% is a fairly symmetric atmosphere, but 10% is significant. A 10% difference in pressure, surface pressure on the Earth, would be a difference between a calm day and a hurricane. So I'm not saying there's a hurricane on Pluto, but there are winds that will be driven by a 10% pressure difference that is significant, winds on the order of meters per second. The lowest 4 kilometers, I think, is very puzzling, and it's telling us something very important about the energetics of how the atmosphere interacts with the surface. And I don't think we understand that too well just yet. It's a fairly complicated problem. Dave Hinson is working on that pretty intensely. Okay, now moving on. I'm going to do this pretty quickly. The ultraviolet solar occultation experiments. Again, entry and exit occultation. This is just the total count rate in the ultraviolet and extreme ultraviolet as we followed the sun through Pluto's atmosphere and behind the planet. And what we see here in white is the plot of the total photon count of the instrument in the forward direction, and just for kicks, the red is in the reverse time direction, just to show that it's very, very symmetric. The atmosphere appears to be very symmetric. At 1,300 kilometers, we saw clear opacity from nitrogen. 800 kilometers, methane. Lower altitude, we can see, and we detected acetylene and ethylene, probably some absorption by haze in that region as well. But it is very, very symmetric. That's also something that I was a little surprised about. I suspected that there would be some strong day-night differences in the atmosphere, but not greatly so. The bigger surprise came here, and I apologize, this is a little bit detailed, but I wanted to show you the expected versus the measured opacity of the atmosphere in the ultraviolet and extreme ultraviolet. The left bottom figure is what we saw in terms of the opacity as a function of tangent height. The top left figure is what we predicted. Almost all the opacity below around 900 angstroms or so due to nitrogen was not there. the number one constituent we expected to be in the upper atmosphere was just essentially absent, to better than 90%. That was a big surprise. But other things were there that we could see. The plot on the right is the inferred column density of nitrogen in black, methane in red, and then down lower you can see acetylene in blue, actually that's green, and then in the blue you've got ethylene. So some things are fairly obviously, they're really high signal-to-noise measurements. In terms of how they stack up to what we expected, and what we see, just a second. Yeah, I want to go to this one first, is that the methane as a function of altitude is telling us a story that seems to be inconsistent with the other trace gases. If you look at just the methane abundance as a function of altitude, it appears to be what you'd expect from a well-mixed atmosphere with a turbopause something in the range of maybe 500 to 600 kilometers above the surface. If you look at the opacity or the number density of acetylene and ethylene as a function of altitude, they give us essentially an opposite story. They are consistent with the model with no mixing whatsoever. So you've got two different stories here, which we haven't sorted out yet. Methane telling us the atmosphere is well mixed to maybe 600 kilometers. Ethylene and acetylene lower down in the atmosphere seem to suggest that the atmosphere up here is not mixed at all. It's just bizarre. I know it looks like spaghetti diagrams, but to an atmospheric scientist, this is really a puzzle. Also down here, we see a profile for these two species, which doesn't seem to fit any model that we have. I suspect there's something interesting going on there with the aerosols in the atmosphere, and I'll come back to that in just a moment. Now, from the nitrogen density, we can get the extent of the atmosphere, because nitrogen is most of the atmosphere. So I'm going to back up and show you the expected versus observed temperature profile. Okay, so the light, I guess that's gold line there, is pretty much what we expected for the temperature profile of the atmosphere. This is from the ground up to about 1,500 kilometers from the center. The darker curve here is our best model of the nitrogen that was observed. So again, quite a bit different than what we expected, and the implications here are just enormous, because the lower temperature that we see in the upper atmosphere means that the escape rate from the atmosphere is just orders of magnitude lower than what we expected, several orders of magnitude. And even the constituent that is escaping is different than we expected. So these two things are giving us some, they're clearly interesting and they're clearly valid observations, but they sometimes lead to things that are just so different that we have a hard time to know how to get our head around them. We clearly have detected trace gases that are telling us something about transport and photochemistry, but we haven't sorted that out yet. A homopause is probably there, but why it's there, we're not quite sure. And then, you know, this connection with mixing, I think that there may be a problem here with our models. Our models may just simply be inapplicable to the kind of atmosphere we're seeing on Pluto. That is, the aerosols are having a dominant effect on the trace gas abundances of these major gases like acetylene and ethylene. And I'll come back to that in a moment as well. Key points, again, the temperature in the upper atmosphere is much colder, the atmosphere is more compact, as Alan said earlier, and the escape rate is just orders of magnitude lower than what we expected. The implications for a captured atmosphere on Charon, which I'll show you in a few minutes, isn't there, or even the capture of a little bit of methane, which might have an implication for the dark pole. In fact, there's essentially no nitrogen escaping from the upper atmosphere of Pluto. It's all methane. So, okay, going on hazes, my favorite topic here. So this is the thing I think that just shocked me. I don't know how to say it. Before the encounter, we were talking among the team members on how to stack images and to pull out details of a thin haze close to the surface. And we were seriously wondering if we could even do it. And then we get images back that show us this grand panorama of a haze that's global and thick and extends to over 200 kilometers altitude everywhere. It has a scale height a bit like that of the background atmosphere. And if you look closely, it's got all these thin embedded layers that are brighter than the background, which is, they're really bizarre, I mean, if you try to model them. And they're coherent. The layers are coherent for thousands of kilometers across the surface. And to me, the most puzzling thing is that they're occurring in the atmosphere all the way up to 200 kilometers, where I showed you a few minutes ago, the temperature is high, 100 degrees Kelvin. This is the opposite of how you should normally form simple haze, single-phase haze, where you have condensation where the temperature is low. And here we have hazes forming where the temperature is high. So let's go back here. Okay, so here's a close-up. I think that you can see here, if you look carefully, the layering in the images and how coherent they are. They almost appear to be arcs centered on Pluto itself. I also remember that after we got our first images, we were trying to argue whether there was one or two layers in the haze. And now you can easily count 20 of them if you're careful. This is a close-up. I'm sure you've seen this before. And this may show the one bit of the haze that we sort of expected, and that is the layer that's close to the surface here. That's at like 8 to 10 kilometers altitude. It is the brightest region in the haze. And that is at the lowest part of the atmosphere where we expected to see a single constituent, single phase condensation of a product that's produced from photochemistry. And the simple picture is here. You have sunlight shining on methane, which produces things like acetylene, which mix downwards, and they hit this low temperature region and they condense. That's probably the only thing that really looks like what we see in this atmosphere. So we've really got some big puzzles here. Okay, moving on. Now this is a little bit technical too, but I wanted to point out that the timescales that control how this haze layer evolves are short. The sedimentation time, so the particles that we see in the haze, are on the order of centimeters per second. The timescales for falling are on the order of tens to hundreds of hours. So there's got to be something that's producing these on a time scale that's shorter than or comparable to the rotation time of Pluto. Again, not quite sure what that is just yet. Now, Alan earlier mentioned that there's a similarity between the hazes on Pluto and Titan. And there are some similarities. In particular, the detached haze layer on Titan, the highest haze layer in its atmosphere, occurs at about 1 to maybe 10 microbars. And the layers that we see on Pluto are right at the surface. If you sort of overplot the atmosphere of Pluto and Titan, you get something that looks like this, and I'm not going to go through all of it, but I'll just point out that the brown profile that's snaking through there is the Cassini-Huygens temperature profile on Titan, plotted as a function of Titan altitude, and over here you have Titan pressure. This thick blue line here is the temperature profile of Pluto that we've inferred, and the haze layer that we see. So the haze layers overlap in pressure, not so much, there's a little bit difference in terms of temperature and gravity, but it's a nitrogen atmosphere, same general mechanisms that you would expect for producing the constituents that go into hazes. Sunlight on Pluto and Titan. Titan has an additional component due to due to Saturnian magnetospheric particles, but that's kind of minor in the grand scheme of things. One thing is nice is that Titan has been studied extensively. Its haze is reasonably well understood in a global sense. And part of the motivation for understanding the hazes on Titan are their connections with tholins that are deposited on the surface. Some of these are simple, some are complex. We have lakes of acetylene and ethylene. And so that whole pathway from charged particles all the way down to lakes of photochemical products on Titan has been fairly well studied. So some of that must map into the atmosphere of Pluto. What part of it does map into it? Well, sunlight will break up methane, and that will it will trigger a set of chemical reactions that form the things like acetylene and ethylene, perhaps HCN and other nitriles. And the ions that are produced in the upper atmosphere will attach to some of these, and that will trigger a growth of monomers of of maybe 300, 400, 500 atomic mass unit nuclei. I call these nuclei because these are big enough then to fall downward in the atmosphere, grow by accumulation of other things in the atmosphere, other trace gases that are there. And by the time they get to the haze layer, they're made up of these photochemical products plus other things that have stuck onto them, and they've probably coagulated to form fractals as well. Now, if you just do a simple mapping of this to Pluto, and I'm not going, again, I'm not going through the details, just what's the bottom line here. If you do the appropriate scaling, we think that we could get somewhere like 3 to 8 equivalent meters of tholin-like materials on Pluto in 4.5 billion years. There are some assumptions built into this, and I'll tell you what those are in just a minute, but it's reasonable that you could get materials like the stuff that you see in the dark areas on Pluto. Sorry, I keep getting the wrong one here. There you go. The dark areas like that, and maybe some of the veneer that you see up here, the reddish veneer. Maybe this is different types of photochemical products that have stuck onto hazes and then settled on the surface. Okay, again, key points. The haze is a complex phenomenon. We don't understand very much about it. Maybe the one thing we do understand is that very low altitude layer. The similarity between Titan and Pluto is encouraging, but we've got to explore the details of that quite a bit more before we're going to say that they're exactly the same mechanism or the same phenomenon. The tholin production mechanism, which is a complex process in itself, may follow a similar pattern, but again, it's a little bit soon to do that. Okay, so what produces the thin, bright layers? And this is something a lot of us have puzzled over for a long time. Again, very uniform spacing, 10 kilometers or so. Maybe 20, maybe a couple dozen of them, maybe more if we could map this higher up in the atmosphere. What produces that? Our leading candidate for an explanation at this point is what Alan mentioned earlier, and that's buoyancy waves, gravity waves in the atmosphere. We see those on Earth when you have thunderstorms and when you have air flowing over a mountain that generates a perturbation and the buoyancy that causes an oscillation. And it does seem to give us the kind of structure that we see in the haze layers. Now, this is a complicated figure, and I'll just point out a few things. This is a model that Daryl Strobel and Schwinzu has put together on the perturbation of the atmosphere, temperature, pressure, density, and also condensation rate as a standing wave would propagate vertically in the atmosphere of Pluto. And you could do some tuning to get about the right spacing between the two. The blue curve here represents a quantity that's proportional to the condensation rate in the troughs of the gravity wave where the temperature is lowest. So this is about our best candidate. But I want to caution you here that these waves in the atmosphere, whatever they are, these layers in the atmosphere, are pretty much globally uniform. And for gravity waves on Earth, we usually associate those with perturbations that are local. We don't see anything like this on any other planet that I know of. It's almost like the atmosphere of Pluto is ringing in a radial direction. And here, just to show this picture, we don't know the details of the geometry of the layers here, but you can see that the layers that go over these mountains here are not wavy, okay? So there's something else going on here. Maybe it's something like a standing wave in a resonance cavity, which is Pluto's extended atmosphere. We just don't know at this point. Okay, Alan Stern has a paper submitted to Icarus, which I think is actually rather profound. And he talked about it at the press conference today, and that is that this is the work done, he and other people, Rick Benzel and their students. What you see is that because of the obliquity variation on Pluto, we expect there to be huge variations in surface pressure over long periods of time. Variations by many orders of magnitude. Now, what does that mean for things like hazes and tholins? Well, when the atmosphere is very, very thin, like what you see in the low pressure results that he gets occasionally in these models. Again, I don't know the details of them. But the pressure is so low that the atmosphere is going to be so thin that tholin production probably occurs entirely on the surface by ultraviolet photons and solar particles that go all the way to the surface. That would produce one type of tholin material. On the other hand, when the atmosphere is really thick, maybe thicker than the atmosphere of Mars, but nitrogen with a methane component like Titan, we may get a full-blown Titan-like atmosphere on Pluto, and you might get a similar type of raining of tholins and photochemical products on the surface that you get on Titan. And Titan has a very complicated set of tholins on the surface. So this could be a very important thing going forward as we model it. Okay, so yeah, I've said all that. Go on. Just mentioned the Charon solar occultation. I only have about 2 minutes. This is the locations of the occultation from the St. Malice experiment. I'm not going to spend much time on it because we didn't see anything. We had a non-detection of an atmosphere on Charon. And from that, we can get an upper limit on some constituents. Things like methane is about 9 picobars, and acetylene, which we did see on Pluto, 6 picobars. But that's about it. And that's just consistent with a very low transport rate of material from Pluto. This low escape rate that is a consequence of the low temperature upper atmosphere and the more compact atmosphere. Okay, how much time do I have? Okay, so just, I can read through these real quickly, or you can read through them. Most of these represent things that were slightly suspected, but mostly surprises. We knew that there was nitrogen and methane and probably photochemical products. The temperature profile at the surface and upper atmosphere is just a complete surprise. The escape rate, the type of escape rate, we spent years developing models of this hydrodynamic outflow from Pluto. Completely have to retool those models. They just don't work anymore. And the escape constituent is methane instead of nitrogen. The haze, I think that we're not quite there in terms of having a complete mechanism yet. Just because looking at Titan's hazes are complex things, and tholin production is not a trivial thing, even though it's not easy to define what you mean by tholins. The gravity wave mechanism, I think, is our best candidate for an explanation for the thin layers. And then, of course, this climate evolution is really cool stuff, no pun intended. I mean, that could lead us to lots of variations in the deposition of different types of tholins on the surface over time. So I guess I'll stop there. Thank you. So questions?
Thank you. Are there any questions? Well, there is one. Okay, well, while you get queued up, I have a question for you. The mechanism for the gravity wave generation, you mentioned that because it looks like Pluto's ringing kind of in a spherically symmetric fashion.
I don't have a mechanism for that.
But if it is a standing wave, as you suggested, then you could probably work out what the numbers are for, say, what the energy release would be, say, at the base of that chamber, because that is one way to maintain that. Have you guys run those numbers and see, like, because that might constrain, perhaps, like what kind of mechanism might be at play?
The one thing we have looked at, which is a piece of what you're suggesting, is the amount of heat that's dissipated by turbulence and mixing, and how that affects the condensation itself. And there's essentially no effect there.
No effect?
No effect at all.
So there's orders of magnitude less?
In terms of condensation and evaporation
I understand.
drivers.
Okay, interesting.
There might be other things. I'm sorry. The answer is no effect.
So let's take the first question there on the left.
The total absence of this dark material on Sputnik Planum suggests that it's not there right now, but based on your latitudinal dependence, it looks like it should be precipitating out on Sputnik Planum. Is that correct?
You're talking about the sedimentation of tholin-type materials onto the surface.
That's right.
That is a very, very slow process. You're talking about 3 meters to 8 meters of stuff over 4 billion years. It would be easy to cover that up with the light frost that's moved around seasonally.
And
So
also if convection is overturning and wiping it away too.
Yeah, so there could be at least 2 things I can think of immediately that could lead to areas where you don't see tholins. There are areas where you see like a light dusting or like a light veneer on top of the ice of tholin material. But I'm not sure it's even tholin material. So we've got a little bit of work to do there.
There are also some dark layers at depth, just to remember that. You see them in the crater walls and in some of the fault scarp walls. So that's an interesting thing about what happens over time with the dark material deposition.
It may be a complex problem that's really hard to untangle, but I think that the layering that we see in the craters, the mountains, all that stuff is somehow tied into the history of the atmosphere.
Hey, Mike, this is
Yep.
Casey
Yep.
Lasapi. I was going to pretty much ask just the follow-up question you just answered, but one point I'd like to pick at is that we have an age for Sputnik Planum of less on the order of 10 million years.
Yeah.
What is the predicted climate frost timescale? What is the cycle
I
period?
think the
Alan's
predicted
paper?
age for Sputnik Planum is an upper limit of 10 million years, right?
No, I'm sorry. What is the climate frost? What is the timescale for the variation between
In transport of frost?
no, microbars? Your point number 8 here. How long does it take to go from microbars up to 40 times Mars's pressure? How many millions of years is that cycle?
Those are in work that Alan Stern and Rick Binzel are doing.
Right.
And a lot of that is on the longer scale climate cycles, like several millions of years.
Right, and that's an interesting number to compare to the 10 million years age for Sputnik Planum. And to see, because if that, let's say 0 to max pressure happens in 1 million years, and you have this tholin production and precipitation, you'd expect Sputnik Planum to have a lot of material on it, which it doesn't. So there's an interesting timescale comparison.
Yeah, again, I think it's going to be really, it's going to require us to have a different set of tools to understand how to quantify that. Because these tholins are very small particles that come down, they're blown around, they stick to each other and to ices, they stick to different surfaces in different ways. And to predict how much is going to go in one place, I'm not sure we're even close to being able to do that yet. Okay. I'm not trying to not answer you. Well, actually, I am trying not to answer you because we don't have the models yet to really answer.
I didn't expect an answer to the question. I was just showing that there's an interesting. We have a piece of information here we should compare.
It is very interesting. Thank you, Casey.
Okay, well, thank you very much. Thank you very much. Give him a hand. Okay, so now I'd like to introduce my colleague, Simon Porter, and he's going to talk about the small satellites of Pluto.
All right, and that's what I'm going to talk about. And here representing a large group of the New Horizons GGI team. So the small satellites of Pluto, when the New Horizons mission was proposed and when it was when work started and when the spacecraft was almost entirely built, Pluto had 1 satellite. And then the summer before launch, just about 10 years before encounter, we found 2 more satellites. So there's Pluto and Charon, and then there's Nix and Hydra, which are still called candidate satellites. And as we'll see, New Horizons brought them from candidate satellites to real places. So these were discovered right before launch, and then using Hubble with ACS, and discovered 2, and that was kind of worrying that, okay, maybe there's more there, maybe there's a dust ring, maybe it's a hazard to the spacecraft, because New Horizons flew past interior of Nix, and we knew that it was going to fly interior of Nix as soon as it was launched. So kept on looking, and then in 2011, Mark Showalter found another satellite over here that was between Nix and Hydra. And now we're really interested. Okay, we got 3 satellites, and one of them is between the other 2, so maybe there's another one in there, and sure enough there was. So then we have Styx, which is interior of Nix. And Styx was really hard to find. Styx is really, really faint compared to the other 2. So you see, Nix looks blindingly bright next to Styx, and you have to really mask out Pluto to see it. So we saw this, and we knew that we couldn't see much those interior Styx, but New Horizons was going to fly interior Styx. So this is the state of knowledge as of last year, pretty much. And then we this was about this time last year. So this is coming in, approaching. So going through April to May, going out to just about 2 months beforehand. We were doing these deep looks, taking with the LORRI image, but we've been at 4x4, so we can bring the exposure time up as long as possible. So you can see Pluto and Charon just absolutely saturated out. Even 100 days away from Pluto, we're can't even get anything useful out of Pluto and Charon. Nix and Hydra start to become blindingly bright 2 months out with this sort of exposure time. But you watch Styx, and it's only, you have to kind of come out. There you go, there's Styx. So it took a while just to see Styx in these images, but we kept on looking, and we found absolutely nothing. So so that seems to be we have the quartet of small satellites orbiting around this inner binary. And that seems to be it. We didn't see any rings. We put pretty high upper limits on the rings that we could see in there. So this is the schematic view of the system. If you're looking from Pluto's north pole, the spacecraft trajectory went through here, so passing very close to the L3 Lagrange point. The trajectory is inclined 43 degrees to the plane. And there's Pluto and Charon moving around, and Styx, Nix, Kerberos, and Hydra. They're very close to being at resonances, mean motion resonances with Charon, but they're not quite at them. Their orbit paths are circular. Their orbits are not Keplerian in their motion because they're so highly perturbed by Charon. So they're pretty closely fit by a Keplerian fit, but with a secular term put on top of it to get everything moving fast. But that secular term is very, very fast. So they're a very complicated system there. And so we didn't find anything in this gap here. We knew that there's nothing interior here. This was previously identified as the Charon instability strip, but we didn't find anything in here where we might have found anything. And we looked out here, but we didn't see much. And the motion there was sufficiently so that this is sufficiently far from Charon that the motion would not necessarily have been in the plane of the system. Here, in this sort of region, it has to be in the plane of the system. It doesn't have to be in the plane of the system out here. So we looked, we didn't find anything there. If there's something on a wacky orbit out here, maybe there's a chance we missed it. This is what the actual motion of the system looks like. And going through the dates here, and watch out from the top corner here. This is the view from the sun, but rotated Pluto north. And then that was the flyby real time. So pretty much we saw the system in a snapshot. We didn't really see their orbit motion we were going through. We saw it on approach. We expected we were just going to see a single face of the objects. As it turns out, that wasn't the case because they are rotating so fast. So these are the objects themselves. These are the best images that we have of all four of them, and the best images we'll probably have for a very, very long time. We got one image of Styx, and there it is. We got lots of images of Nix because if you go back, there we are. Nix was actually on the opposite side. So all these ones here, we were actually technically doing a night side flyby. That's why we have these nice half-angle images of Pluto that we can see these beautiful hazes and everything. But all these satellites are over here, so we're kind of looking back towards them. Whereas Nix, we passed through very close, passed through at 9 degrees phase angle. So we got very high phase angle observations of Nix, as well as half angle observations, as well as departures. And Nix we got a lot of, and then the rest of them we got much less so. So this one is at about 9 degrees of phase. These are all rotated, so Pluto north is up, and I'll try and, for the most part, that's true for the rest of these observations. They're rotated to be Pluto north up, which is arbitrary. But it's uniform at least. And then we have Kerberos. We have two images of Kerberos. This is the better of the two. It really looks like two kind of objects, but sort of sketchy enough. And then there's Hydra, and we'll talk about Hydra. Oh, there it goes. Okay, so for Styx, in addition to that image, what we've got is the light curve. And the light curve is kind of noisy because it's kind of faint. But you can see it's a nice double-peaked light curve, and John Spencer was able to fit a period there of 77.7 hours. This is significantly faster than what we expected. We expected all of these small satellites were going to be close to synchronous, so close to their rotational, their rotational period would be close, but not quite the same as their orbit period, and then they would sort of slowly wobble around from there from perturbations from Charon. That's not the case at all. They are all significantly supersynchronous. Styx is the second slowest, and it's 77 hours. So, you know, it turns out we can actually go back and find these periods if we look at the old Hubble data, but we never thought to look for periods this short. There we go. So the long axis that appears from this image, and then matching that to the photometry, it appears that Styx is about 13 kilometers long by about 8 kilometers. It's a sort of elongated body. It's about all we can tell with it. All right, so here's the light curve for Nix. You can see the error bars are much smaller on here. And you know, a simple model doesn't fit nearly as well, but massive amounts of light curve variation on it. So we knew that very early on, that Nix had huge amounts of light curve variation. So we were probably seeing Nix at the equator. And sure enough, we were. Its period there is at 43.8 hours, at least during encounter. And these are the best images the best 6 images we have of Nix. Scaled up here, the scale bar is wrong. That is 20 kilometers. So the width of Nix is about 25 by 50 kilometers. So it's about 2-to-1 axis ratio. And again, these are Pluto north up. So you can see between these 3 observations, you're seeing that long axis is this way. Remember, Pluto's north is up here. So long axis is this way. And you can see this big crater here. We don't have any names, formal or informal, for features on the small satellites. So I'm just going to call this Big Nix crater. So you can see Big Nix crater is kind of in the center here, and it goes down. So right away, you've got sense of motion. The sense of motion is going this way. And so the pole of Nix has to be pointing that way. Pole of Pluto is that way. So you can see right away, it's about 110 degrees away from Pluto's north pole. Whereas this one is not so lumpy, because this one, we're seeing it down the pointy end. And this is the first image we got back. So we got this image back and thought, oh, Nix is round. How are we getting so much massive light curve? Then we got this one. So this is looking down the long axis. This is looking down the short axis of it. This is looking down another aspect of the short axis. This is actually our LISA ride-along. Now, we have LISA scans of both Nix and Hydra, and the Nix one's going to be a lot more interesting because it's much closer. They're not on the ground yet, but keep tuned because this one will eventually have a full compositional map for it. Not great resolution, but it will be compositionally mapped. And then this is the one MVIC image that I'm going to show actually today. And it looks a bit small. It looks much better if you scale it up, but this is just scaled to be the same scale as these because you're basically seeing that little chunk there. But this one is at almost half phase, and you can see tons of craters on there, and Kelsey Singer just talked about this in the press conference, that there are tons of craters we're seeing on here because they're suddenly seeing shadowing. This is at 9 degrees, so you can't see the craters very well. So this has tons of craters on it. Looks like a really old surface, which is, it means these things must have been around for a long time. They can't be that many generations of satellites unless this is all intra-system impacts. And then we have this final little departure image here, which doesn't look like much, but is actually very, very helpful in constraining the phase function of the surface. And we do have a couple color images of Nix. This is the second best, but I did it because it's got Big Nix crater in the middle. And you can see, now, Laurie's panchromatic. It's completely unfiltered CCD. So we're just seeing the CCD response function is our bandpass here. Whereas this is the enhanced color. This is the same sort of enhanced color that Will was showing earlier. You can see this area isn't just dark because it's shadowed. It's dark because it's actually a different material. So we're seeing compositional diversity on the surface of Nix, which did not really expect. We don't know why this is red, but it's red. And then the rest of it is pretty much white. Hydra, We have similar scans. Hydra is pretty much the same sort of white color, very high albedo, and then this darker albedo red stuff. So hopefully we'll be able to get a bit more details when the LISA scans come down. Here's Kerberos. Kerberos is not much bigger than Styx, but it is a bit brighter. So we were able to get a much better light curve for it. And it is the slowest rotator of all of the four. And that's the light curve. And we have 2 images of it. So we're doing better than Styx. And this is the first time this one's been released, because this one came down back AGU week. And then we have this sort of lumpy one that you saw before. So this one doesn't show lumpiness, but it's also from about twice the distance. So it could be lumpy, and we're just not resolving it quite as well as this. So yeah, it looks like it could be a bilobe body. It's not that different in size from some of the comets we've been to that are bilobe in shape. Is this a merger of 2 bodies, or is it like CG? We don't know, but it's intriguing, just enough to know that it's complex shape. And here's Hydra, and this is an annoying looking light curve. And this is not even a very good fit to the light curve, and this is a lot of CPU time to get this fit. So you can see, and I've been changing the scale bars here for each one of these just to maximize the amplitude, but this is not a high amplitude light curve. And we knew that going in when we were doing the approach imagery, that it was not varying in brightness too much. So it was either round or we're looking at the pole, and turns out we were approaching Hydra on its south pole, very close to it. And it's also not a very ellipsoidal body, so we're getting 2 different peaks in there. They're very different heights, 2 different troughs. They're very different heights. And it is a very fast rotator. It is a 10-hour period. It is extremely fast. So it is fast even for a KBO, pretty much. We have no idea why it's spinning that fast. And here are our 4 images. That one is being released for the first time here. And then we got this one on approach. This one kind of looks like a mitten. And then this is the best image. And this one was kind of lucky. We took a mosaic, and we didn't know where it was. We just did this big 6x6 mosaic, and this guy showed up right on the overlap of 4 of the mosaic footprints. So it was just perfect. And because it was in the mosaic, and because it spins so much, we can actually see a bit of motion in that one. So we get sense of motion from that. So we have sense of motion. We know we're looking at the south pole of it, but from that. But these phase angles are not too different. So this is clearly a very complex shape that we're seeing here that's rotating underneath the spacecraft as we were on approach. So Alan showed this earlier, and these are really, really super synchronous objects. Something has either spun them up, well, something definitely spun them up. Something might be keeping them spinning, or maybe the impacts are sufficient to do it, and they just can't despin enough. It is a very complex tidal state. And making this tidal state even more complex is that this is kind of a bit of a lie, in that this animation kind of shows it such that all their poles are pointing up. They're pointing in the same direction as the Pluto-Charon pole, which is the same direction as their orbit pole, but that's not true. If you look, here's Pluto's pole. By a coincidence of nature, Pluto's pole points at Earth's equator. So here's Pluto's pole, and then this dashed line here is 90 degrees away from Pluto's pole. So if you're below this line, you're prograde rotator, and if you're above the line, you're a retrograde rotator. And they're all retrograde rotators. And the closer they are to Pluto, the more retrograde they are. So Hydra is almost in the plane of its system. Kerberos is up above it. Nix is more up above it. And then Styx is right off. So this sort of trend here, 3 points gets you suspicious, 4 points makes you really, really suspicious. This is probably some sort of tidal end state. But that's going to take some very complex modeling to actually figure this out, because this is like nothing else in the solar system dynamically. We only have one really chaotic moon in the solar system, and that's Hyperion. And this is a very different case to Hyperion. And I say chaotic because we got that 44-hour period for Nix. Mark Showalter went back and looked at his photometry from HST in 2012, which he used to discover Styx. And he fit a period for Nix, and it was 48 hours. That was only 3 years beforehand. So its period changed by 4 hours in 3 years. That is really kind of terrifyingly a lot of perturbation there. So it is really tumbling a lot. And this is going to be a very complicated tidal state to figure out. These things must not be dissipating almost at all, but they're very strongly perturbated. And again, this is the one that we're going to get the LISA scan for. So just wrapping this up, Pluto's 4 small satellites are very complex objects. They're not just simply dots of light anymore. They are actual places. And they have complex surfaces with lots of craters on them that show that they're an old age. They are complex shapes that don't necessarily make sense. They are extremely fast rotators with poles that are misaligned to their orbits unless they're actually quite aligned. If this is some sort of tidal end state that we need to figure out. And something that needs to be emphasized that these talks in this session are based on based on the science papers that came out, and they are open access. So this is based on the Weaver et al. Paper, and that will give this URL will give you to the full text of the article, and from there you can go to the other articles from the rest of the session. So thank you very much.
Thank you, Simon. That's excellent. Are there any questions? Yeah.
Just a quick one. Is that animation available also as supplementary info?
Yes, it's on YouTube.
You can get it on the JHU website as well.
Yeah. Hey, do you know if the red stuff on, Nix is the same red stuff that's on Charon?
No, we don't know, but we might be able to tell when we have the LISA scan, or maybe not.
Okay.
I've been calling that crater Big Red, by the way.
Yeah.
Big Red.
My question is in regards to having it spun up. I was just wondering if maybe the size, if you guys had considered perhaps the York effect, if that had...
No, so York doesn't work out here. The sun's too weak.
Oh, so it's too far away. Okay.
Yeah.
All right.
Yeah, so York doesn't work for KBOs. The sun is just too weak. Okay. So unless Pluto were to become a brief sun, you don't have quite enough radiation to do it. So yeah, this has to be impacts that are driving it up.
John's still there.
We don't know if that's impacts from a disk from original material or if it's impacts later on from KBOs.
Simon, over here.
There. No, there you
Hi. Can you go back to the new picture of Hydra? That's where my question lies. And I was going to ask your opinion. Is that dark splotch a shadow or albedo?
Yes, it is a shadow. Okay. And if you go down to my poster, you kind of see a shadow in my shape model.
Excellent. Okay, thanks.
Does that shadow line up with anything on the best resolution picture or no? Is it that feature?
I think it's actually that.
Okay, that's what I was wondering.
Yeah. Yeah, it's some sort of canyon that's going across there.
We can call that one Simon Crater.
I'm not dead yet.
Yeah. We'll go to the left and then back to the right.
Hi, Simon. Oh, that image of Hydra is just fantastic. I just wanted to point out that something we were showing the periodicities for the 4 different moons, and something I guess I hadn't appreciated before. Kerberos is slow enough; it's almost moving synchronously with Pluto and Charon. At the other extreme of Hydra, which is tumbling like crazy.
It's close.
It's not there,
but it's not
close.
quite. Yeah. It's close. It's sort of. It looks kind of close by eyeball, and then when you look at it, yeah. So there's that may be that definitely is one aspect of it. It's probably about 8 different sine functions that are added together, and that's how you're getting the chaos.
Yeah. Fantastic.
Just quickly, are you expecting any more images of these 4 satellites to come down?
So for Hydra, there's like one that's about like that's left, and then we've got one more for Nix that's around this era, or around that resolution that's left. So as far as LORRI images, that's what's left. The major thing that's left to come for the small satellites is the LISA scans.
I have a question. Would you care to speculate wildly as to why we have such funky spins in this system? And might Charon's lumpiness might play a role in this?
Ooh, I don't know if Charon's lumpiness will play a role. Charon's existence plays a role. Charon's perturbations. So I think these might be primordial spins, and just the perturbations for Charon are sufficient that you're never able to drive up enough stable tides to dissipate within the moons. And you can't pull, and they're not big enough to pull up any tides on Charon. So you're not pulling up tides on Charon, they can't pull up any tides, you're not dissipating energy, and so you just preserve it.
So is it possible that it's continuing to spin up? Or even more wildly or chaotically?
Well, Nix actually did spin up.
Yeah, right.
But it's probably trading energy with its orbit.
Right.
John.
Yeah. So I haven't calculated the tidal damping time scales that you would expect for these guys, and have you calculated that?
It's tricky, yeah, because you're not setting up static tides like. Because of Charon, if Pluto and Charon were a single object, you could just use that straight tidal time scale. But you're not setting up a single tide in there. You've got 2 interacting tides from Pluto and Charon in there, and so a simple Q tide model is not really going to be physically realistic.
Yep.
Over here.
Hi, David Hamilton from York University. My question was, when you're publishing orbital radii of these smaller objects, do you do so from the barycenter of the Pluto-Charon system or from the center of Pluto?
Well, so you do. So their orbits are barycentric relative. They're not Keplerian. So you can put sort of mean relative parameters, assuming a single body in the system. But really, what you publish is state vectors relative to the barycenter, because that's the most honest thing you can publish.
Thanks.
Any more for Simon?
Any more questions?
We have a couple minutes left, so if anyone has questions for the other speakers who are sitting up here awaiting your questions.
Oh, yeah. On standby.
Yeah.
I'll ask a question. These orbits look pretty circular. Yep. So, you've alluded to the possibility that Charon is somehow affecting the spins. To me, it seems the most obvious thing, you'd be getting eccentricities on these orbits. So you want to comment on that?
There's very, very little eccentricity in the orbits.
Yeah, that's what's surprising. You want to comment on that?
Well, if there were any eccentricity in their orbits, they would destabilize because they'll start to interact with each other at a certain point. Nix and Hydra, if Hydra were where Kerberos is, they would destabilize each other. They're just big enough. If you run over the age of the solar system, and there are very narrow windows where Charon's perturbations will just constructively add up and destroy them. And if their inclinations are a bit too high, then they'll trade with their eccentricities, and then they'll start to run into each other. So, they're spaced out, but they're about spaced out where you would expect them to be spaced out. If you just plop one of them down, and then you can populate out where the rest of them are going to be based on that. So they pretty much do have to be in circular orbits in order to survive for the age of the solar system.
What is the ratio of the kinetic energy of rotation and orbital kinetic energy for each of these bodies?
I don't know, because we don't really know what their masses are. We have ideas for their masses from interactions, especially for Nix and Hydra, but their error bars are about the size of the masses, so we don't quite know exactly.
Yeah, you mentioned very interesting thing that maybe you can have exchange of energy between rotation and orbit. If you long-term track it from Hubble telescope, maybe you can see the...
Yes, well, after seeing that change, there is a very strong motivation to continue monitoring it with Hubble photometrically.
You mentioned that impactors could spin up these objects, but could things that are passing by without impacting also spin them up?
Probably not, because they're going to pass by so fast and so briefly. It's not going to pass by as fast as New Horizons, but they're going to pass by, very briefly. And if an object were, an object would need to be very, very large in order to spin them up.
And if it were that large, would it perturb the other orbits of Pluto?
Yeah, it would actually perturb their orbit and then destabilize the system, and then they'd run into each other.
Simon, you didn't say too much, or maybe I missed it, about the colors of these objects compared to Charon, Pluto, or KBO's.
So holding off a bit until we get the full compositional information, but for the most part, they're flat, but bright. So Nix and Hydra are single scattering albedos of around 0.9, 0.86, except for that area around the big crater, which appears to be redder and darker. And by darker, it's single scattering closer to 0.6.
So do you have MVIC data for all 4 of them, or just the Lori panchromatic?
We have MVIC data for Nix and Hydra, but in the color bands, and we don't have the LISA yet.
Thanks.
Okay. Yep. All right.
Well, thank you very much, Simon.
Yep.
So before I introduce our next speaker, I'd like to ask you all to remember to give these back to us, because we're running statistics, see how long these are. So we'll have people at the doors there collecting these on your way out. So now I'd like to introduce my esteemed colleague, Professor Bill McKinnon, and he's going to be speaking to us about the Pluto-Charon system revealed geophysics activity and origins.
Okay. Okay, we've seen many surprises. You may have read or heard about many surprises, fascinating, incredible, ongoing geology on Pluto, a fascinating history of geology on Charon. The satellites, surprising spins, but also surprising, there are, in the famous words, no new satellites to be discovered down at the kilometer scale. The atmosphere is different than we thought. Even geophysically, Pluto and Charon are a little bit different than we thought. We were hoping to see at least a fossil oblateness. But I'm not going to talk so much about these surprises. I want to talk a little bit about the context and the origin of the system from the data we have. And of course, Pluto is, of course, as Alan began this whole session, it's a member of the Kuiper Belt. So that's where it was born. But what have we learned about Pluto and Charon that actually informs us, or about this process? We have both properties now, so we can actually ask these questions about the origin of the system. Does it actually fit in with the giant impact that Alan mentioned, or is there another possibility? Alan also mentioned the great age of the satellites and the origin, and so I want to talk a little bit about that and about the background about how we can tell time in the Kuiper Belt from craters. And we'll talk about the biggest crater I think we see in the system, and that is the basin that holds Sputnik Planum, informally named, of course. And finally, a little bit about what we think we understand about the insides of these bodies, their differentiation state, the ever popular idea of internal oceans, and to me, one of the most fascinating aspects of Pluto's history is its history of glaciation. Not just the ongoing glaciation we actually see, but the history of glaciation. And finally, ultimately, I'm going to ask the question, what is Pluto? So, here's a couple of graphs. The top graph is plot of known Kuiper Belt objects as of 2008, semi-major axis versus eccentricity. The red dots are non-resonant objects. The black dots are resonant objects. Pluto is a resonant Kuiper Belt object. It's a dwarf planet. It's enthralled to Neptune. This entire structure, semi-major axis, eccentricity, and inclination, is very complex and very organized, and in fact can only be explained through a kind of dynamical instability model, which generically goes by the name of Nix model, where it originated from. But there's basically, the structure of the Kuiper Belt demands that the solar system underwent a phenomenal reorganization at some point in the distant past, leaving and creating the Kuiper Belt that we see. And Pluto is part of that story, and in fact was a very important part historically. And in fact, the bottom graph is a model simulation from the same paper. And here, just to remind everybody, this is one version of the Nix model in which the giant planets are much closer into the sun. There's a remnant planetesimal disk. At some point, the giant planet orbits become unstable. They scatter the planetesimal disk. The new orbits that settle down are the ones we know and love. And there are small dots that survive. This is the Kuiper Belt. And Pluto is in the Kuiper Belt now, but it started in this planetesimal disk. And from all of the variations of the Nix model and its extension, Pluto accreted, we think, not where it is now at an AU of around 40 AU, distance on semi-major axis of 40 AU, but in fact somewhere between 15 and 34. So it had a history, an earlier history, closer to the sun. If we look at the Kuiper Belt and centaurs, objects scattered from the Kuiper Belt, and as a function of density and diameter, we now know where Pluto and Charon fit in from the New Horizons encounter. They're over there. They're actually close to each other in terms of density, much closer than they are to other bodies of the same size, like Triton or Eris and Haumea. They're all around 2 grams per cubic centimeter, but they're clearly different. Some of that could be explained, let's say in the case of Triton, by having higher pressure ice phases or a deep high pressure ocean, but not all of it. Eris and Haumea really are more rock rich than Pluto and Charon. The interesting question though about origins is whether Pluto and Charon are actually different or are they the same? One way we can look at that is by doing internal structural models. These are simple models just designed to get at the rock to ice ratio, where ice stands for all the ices, it stands for organic matter. We're just looking kind of at bulk composition, assuming and I'll come back to this point a little bit later, that both bodies are differentiated. And when you do that, the 10% difference in the densities of Pluto and Charon, and I should say that the sizes and densities have been updated from the original science paper in October. There is a paper submitted, a very detailed effort led by Francis Nimmo and a number of members of our team to really refine the radii of Pluto and Charon. Anyway, the rock to ice ratio of both bodies, they differ from each other by about 10%, but on the whole, since Pluto is most of the mass of the system, 2/3 rock, when you count rock as anhydrous or dry rock, solar system composition rock, and the other 1/3 is ice. But could the difference, the 10% difference between Pluto and Charon actually simply be to something like the self-compression of Pluto because it's a larger body? We can look at that in a couple of ways. We can say, well, let's take the rock mass fraction of Pluto, and let's the ice mass fraction of Pluto, and arbitrarily densify it, increase its density so that if the ice gets denser, you need less rock. So that means the bulk mass fraction of Pluto would drop as you make the ice denser. In order to make Pluto coincident with Charon within the Eris, you'd have to increase the ice density in the entire mantle of Pluto by 100 kilograms per meter squared. That's essential. It's equivalent to melting all of the ice, which is not really plausible for Pluto. So it's not a question about, we can't rationalize, or we can't make Pluto and Charon the same by having a bigger ocean, let's say, on Pluto. Of course, we could go the other way around, and I mentioned this in previous meetings. We could take Charon, and we could take its ice mantle and reduce its density, therefore requiring more rock to make the overall mass budget for Charon. So if we imagine that Charon's ice mantle were porous, we could then, as you decrease the density of Charon's ice mantle, we could make Charon, at least within the Eris, coincident with Pluto in terms of rock mass ratio. But again, you'd have to decrease the ice density by about 100 kilograms per cubic meter. This is equivalent to around a 10% porosity. Now, that would have to be through the whole mantle. And there are things in the solar system that are that porous. In fact, the lunar crust is 10% porous, but we'd have to do all of Charon's ice this way, and it probably can't work. So my judgment, anyway, is that Pluto and Charon rock, the rock fractions in these bodies are actually different. They're close, but they're not the same. And there are more details of this kind of modeling in a poster that you'll see tomorrow. The close coincidence, but not perfect coincidence, of the rock fraction in these two bodies is amplified when we look at the satellites. And as Simon was just pointing out, these bodies are bright, and we presume they're icy because their geometric albedos are so high, maybe 55% in some cases, rising to maybe 85% in the case of Hydra. We then, because these are kind of rubbly, cratered worlds, we assume that because they're so bright that they really must be made almost entirely of water ice. Volatile ices would escape at these super low gravities. We infer that they're water ice rubble bodies. Of course, we don't have the color, the LISA data that Simon just mentioned, so we're waiting to get that. So we're waiting for that kind of confirmation. The fact that these satellites are very icy, though, is a key discovery of the New Horizons mission. The giant impact model has many flavors. The person who's worked the most on it is Robin Canup. You can make a Charon in a slow merger of two precursor bodies in the ancestral Kuiper belt in different ways. They could have different mass ratios and different rock abundances. But the only way that Robin has found so far to make small satellites is if the bodies are partially differentiated to begin with, and they have basically blue, in this case, blue ice shells. The shock waves blast the ice bits off, and then you have Pluto and Charon. It's 30 hours later, and all these little blue bits then, in this smooth particle hydrodynamics calculation, this settles into a disk, and you ultimately accrete a set of icy satellites. That's the prediction. So you can at least say that the Pluto system passes the consistency test with the giant impact model. Another proposal for the origin of binary bodies in the Kuiper belt has to do with the newer ideas about the so-called streaming instability in the solar nebula, where you have it's a collective instability of smaller bodies, nominally called pebbles, that in the gas, the nebular gas, then can clump together and collapse by gravity and make large asteroids or large Kuiper belt bodies right from the get-go, while the solar nebula is around. And Nesvorny et al. Proposed, in fact, you can make, if you had sufficient angular momentum in this cloud of little green bits here, you could make a binary, and then you'd have other small bits around. You could imagine making a Pluto-like system in this cartoon over here. But the streaming instability and pebble accretion predicts, in a straightforward way, that Pluto and Charon would have identical compositions of primordial Kuiper belt stuff, and the satellites would be the same way, and they would resemble, in fact, Kuiper belt bodies elsewhere in the solar system. So they would be basically dark. But none of that's true. Basically, the dissimilarity of Pluto and Charon and the small satellite iciness rule out, anyway, the streaming instability model. And we can say that the giant impact model is still consistent. Now, of course, there are a number of further implications. I'm not going to read all of this to you. The fact that at least right now, the best model works with a partially differentiated precursor bodies that collide is consistent with accretion that's a bit slower, a bit later, so there's no aluminum-26 or very little of it left. So you don't get to totally differentiate it. So if you had total separation of ice from rock, the model actually won't work. And this is, anyway, it's consistent with Pluto accreting, and in fact the giant impact happening in the outer part of the ancestral Kuiper belt, okay? I want to point out one very interesting problem about the small satellites, Styx, Nix, Kerberos, and Hydra, is that even in the giant impact model, when you make the small satellite system, it's generally close in, much closer in than it is now. And you rely on some sort of orbital evolution and resonant capture with Charon to move the satellites out to where they are. And there are a number of papers about this, and they all have a lot of problems, and nobody has been able to solve this actual problem, although there are different proposals. Simon mentioned that the lobes of Kerberos suggest to him that there might be mergers. Hydra's shape is certainly very irregular. It also suggests to me that mergers have occurred. I think part of the problem in trying to understand the origin of the small satellite system, which is in fact a wonderful dynamical puzzle, is in fact trying to just say that these are the 4 small satellites that formed in the beginning. I think it's just as likely that there were more satellites. They evolved in different ways. There were in fact those dynamical instabilities that Simon talked about. But of course, an instability in this kinder, gentler satellite system is not so bad, because the actual orbital speeds are rather low, just a little bit over 100 meters a second. So if you have mutual collisions, they're not shattering, okay? They're accretional. Basically, bodies will merge. I suspect that Hydra and Nix have been dining on other small satellites throughout their history, and that Styx and Kerberos better watch their backs. This also brings up an interesting question. If we think of Pluto and Charon as the origin, as an analog for the Earth-Moon system, the Earth almost certainly had additional small satellites after our giant impact, beyond the Earth's orbit, beyond the Moon's orbit. Of course, as the Moon moves out, it can accrete them or cause them to be ejected from the system. Maybe they accrete to the Earth. If you actually built a complete model of the Pluto system and applied it to the Earth, you would find that the distant satellites, the SNICA satellites, would actually be in the outer half of the Earth's heliosphere, therefore subject to tidal stripping. So maybe that's why we don't see such things anymore. The satellites are not just bright and icy, but they're also heavily cratered. Well, heavily cratered in really, if you actually look at the numbers, means 11 craters, but it's a small pit of real estate, and the cumulative crater density, as Kelsey counts, is actually quite high. And so that's why Alan said earlier that the surfaces of these satellites are quite old. We in fact estimate at least 4 billion years, and that means that the impact that made these satellites happened at least 4 billion years ago. But, where does that number come from? Why do we even say these things? So I want to digress just a bit about cratering in the Kuiper Belt. I had the opportunity to work with Sarah Greenstreet on her PhD thesis, or be kind of a third wheel on it. She looked very in detail, working with Brett Glabman at UBC, about the different populations in the Kuiper Belt that crater things. Okay, there's a whole bunch of different things. The overall impact speeds, these are normalized histograms for different subclasses of populations, are around 2, maybe 2.5 kilometers a second. It's not fast. The big blue one are classical Kuiper Belt objects, and then there are resonant objects as well. These are just different distributions of impact speeds for different dynamical populations. Telescopic observations tell us the relative amounts of the bodies, and then you can use code, ERPIC calculations to determine the flux of bodies, in fact, even how they evolve through time. And what you find is that Pluto is cratered dominantly by what we call classical Kuiper Belt objects. There's a good proportion of the resonant bodies that are with Pluto, the so-called Plutinos, and the 3-2 resonance with Neptune that also crater Pluto. And the important thing is that the scattered disk population, which is the population that evolves to be the Centaurs, that evolves to be the Jupiter family comets, that hits the satellites, provides the heliocentric cratering on the icy satellites of the outer solar system, basically is unimportant for Pluto. It's like disconnected. And you might think, oh, this is a terrible thing. How are we going to figure out anything at all? Well, there's more. When we look in the Kuiper Belt, we need telescopes, okay? And what we see, the bodies we actually count, are big ones, 50, 100 kilometer and larger scale bodies. We actually have a good census of the different populations at these scales, but we do not know what the small KBO population is at all, because we cannot see these bodies at all. So you have to extrapolate from what is known to what is unknown. And so what we did in this paper, Greenstreet et al., what Sarah did in her thesis, is that made different assumptions about how you extrapolate. We know that the Kuiper Belt population is steep at the large end and is flatter at the small end, and so a simple, basically, break in the power law distribution we call a knee. We could drop that down by just a fixed amount, in this case 6, we call it a divot. The bottom, the way to look at this simply is that we looked at 4 different models for how to extrapolate from the big KBOs that we know about to the small KBOs that make the craters we count. They're all anchored at the same end of the large KBO distribution. we assume that all of the subpopulations follow the same size frequency distribution, which is not a bad idea for most of the population, because most of those populations were implanted from closer into the sun. So they all have ultimately the same origin, except, of course, as Alan said, the cold classicals, which we think are in situ, although people argue about that. We calculate the cratering rates using standard cratering laws. We have time histories for decline, and we basically have, when we say we have an age for something, what we have are 4 different model ages. And the way we look at things is that if all of those ages are 4 billion years or more, that's what we say. It's old, it's 4 billion years. If all of the ages are younger than something, let's say 10 million years for Sputnik Planum, that means it's really young. It only gets tricky when you're kind of in the middle. In detail, for the small satellites, we find that 3 of the models all give ages that at least go back to 4 billion years. There is one young age, but that's the population proposed that it's very steep at the small end, and we don't see evidence for that steepness in the crater distributions on Pluto and Charon, and so we don't give that model much weight. Now, I say 4 billion years because, well, we don't actually know when the instability occurred. The thing you take away from the Nix and Nix-like models is that it's happened, this really did happen, but we don't actually know when. It's conventional to say it's part of it caused the late heavy bombardment, and maybe it did, but it's not a requirement of the instability itself. So that's where the 4 billion years comes from. Maybe it's 4.1, maybe it's 3.9, maybe it's 4.3, we just don't know. Not only are the small satellites old, but Pluto's crust itself is probably fairly old, and John Spencer showed this earlier. These are counts by Stuart Roberts. If you know Stuart's work on Mars, you know he can count craters like nobody's business, okay? And the colors here are actually, it's a scale bar from high confidence, where anybody in this room would identify something as an impact crater, to things that are just really too blobby to even believe. Okay, but you can see that there are great variations in the crater density across Pluto. Part of this is obviously incidence angle, part of this is resolution, obviously, because it is a flyby, but part of it is real. The lack of craters in Sputnik Planum, the heavy cratered parts of the informally named Cthulhu Regio. But there are enough craters on Pluto, and indeed on Charon, to say that the cratered parts, the heavily cratered parts on the 2 bodies, also go back to 4 billion years in 3 of the 4 model ages, and we just don't believe the 4th model age, which is much younger, because it requires a very steep population index at small sizes, which we don't have evidence for. The one crater that's not on this chart is, in fact, the basin that holds Sputnik Planum, and John Spencer mentioned this as a possible impact basin. This is one of Paul Schenk's DEMs. There's some noise in the middle where you can't get a good stereo lock, but basically it is in fact not so much a planum, but a low-lying planitia. We'll have to change the name eventually, I suspect. And it's elliptical. And big craters, basins on the terrestrial planets are often elliptical, and for good reason. In fact, we can even tell the direction that the impactor came because of the kind of notch that you see towards the southeast in this picture. The comparison is there to Hellas. Oblique impacts make structures. They make oblique craters, and then parts of the impactor go downrange, and you get that gouge. And I'll point out that the reason we see ellipticity in things like Hellas, or the South Pole Lake Basin, or presumably with Borealis on Mars, if that's actually real, is because these are very big craters, and the cratering efficiency, if you like, is very low. And the transition to ellipticity is actually you don't have to be very oblique to get an elliptical crater, as long as your cratering efficiency is very low. In this case, cratering efficiency is defined as the diameter of the it's the ratio of the radii of the diameter to the impactor, and it's actually a very low. I won't show you all the details. The estimates for Sputnik Planum are it's actually a fairly low number, around 2. That is, for the transient crater that made the Sputnik Planum basin, the impactor is about half the size of the transient crater, which is a fairly small ratio. But that's just sort of fun. Let's see if I can get this to go. And I'll also say there's a talk by Davies and Stewart tomorrow on making big craters on Pluto. And I'll just point out that if you actually look at some of Sarah's cumulative crater densities predicted for Pluto as a function of age, this is for a couple of the models, the knee and the divot. It's at the large end where Sputnik Planum lives, it's all the same for all the models. You actually see that in order to have the chances of getting a Sputnik Planum as an impact crater on Pluto in the past 4 billion years are less than 1%. So SP itself is a very, very ancient structure. I want to talk a little bit about the insides of these bodies. I won't have too much time to say too much. One of the things we know, well, they look like they're differentiated from all the different geological activity and the interesting materials that are on the surface. If they were undifferentiated, Pluto especially, that have a lot of high pressure ice phases, and as the body cooled with time and didn't melt, because you're saying it's undifferentiated, the ice 2 would grow at the expense of ice 1 and ice 5, and the body would actually shrink, and the tectonics on the surface would be compressive. We don't see this, okay? It's opposite to what is seen. As John Spencer showed, we see extension. But you can actually say more. If you actually look at Pluto's thermal evolution, even if you assume it is differentiated, you find that these are temperature plots that start from the surface at 40 Kelvin, and they drop down as 2 billion years ago, 750 million years ago, 250 million years ago. You actually find that this curve might actually drop into the ice 2 phase in the lithosphere. So you'd actually, in this case, also start to get compression and tectonics associated with that. But that's probably not what happened. In fact, it's even worse. Here's one where this is Pluto's temperature profile today, and you just change the surface temperature, and if 37 is the number right now, so you would expect to see ice 2 in the lithosphere of Pluto, but you can get around this problem as long as the effective temperature at the surface of Pluto is a little bit higher, which it really is because you have these ices on the surface that have very low conductivities. Plus the heat flow, these are for steady state heat flows, plus the heat flow is actually somewhat higher because a rock core on Pluto will have fossil heat that is still leaking out. So the fact that we don't see compression, old tectonics on Pluto or on Charon tells us that this transformation to ice 2 is not occurring. And these are just pictures from the Moore et al. Paper, which just came out in Science. All of the tectonics through time on Pluto we see are extensional. So it's a different environment. It's not ice 2. One of the ways you get extension, of course, is through ocean freezing and in the volume change and the phase transformation. It's not the only way to get extensional tectonics. But we think that the extension that John Spencer showed, the incredible rupturing of the older part of Charon's surface, and then the subsequent replaning of Vulcan Planum, informally named, is much more consistent with, in fact, ocean freezing and eruption of ammonia-rich materials to the surface. And this is where a water ocean could exist in Pluto. And this is an idea that's been around for a number of years. It's certainly possible, okay? And in fact, if you add ammonia to a system, and this is a paper again from 2006, it stabilizes an ocean that's even thicker. So the combination of conductive gradient and ammonia makes an ocean almost inevitable on Pluto. But Charon's a smaller body and is likely to have gone much farther along in the freezing process. I have just 3 more slides, so I'm just going to take the time. One of the things that I thought was really fascinating about Pluto was not just that we have flowing material, like Alan showed and John showed, at the margins flowing out, flowing in, maybe convectively turning over, but when you look elsewhere on Pluto, you see all of this evidence for incredible amounts of erosion, and you saw these pictures before. Glacial activity almost certainly caused all of these features to form in this way, but this is in Pluto's past. But Pluto does not have flowing glaciers in these regions now. So what's going on? The obvious thing is, in fact, what Mike Summers mentioned, is that Pluto's atmosphere is not just as we see it today with 11 microbars, but like Mars, goes through oscillations because of Pluto's high orbital obliquity and its eccentricity of its orbit. And in fact, its atmospheric pressure can go up and down. We have evidence elsewhere on Pluto, what we call washboarding, that in fact there may in fact be dune fields on Pluto. So we think the atmosphere in the past on Pluto was thicker and may be thicker again in the future. In fact, there's a couple of talks on Wednesday by Howard and Ermahan on this particular topic. I'll just, second to last slide, I just want to point out, you can even understand this quite simply from the radiative balance that controls Pluto's atmosphere. The sun shines on Pluto. Here's Pluto today. When it comes to perihelion, its spin axis is basically perpendicular to the sun. This is a classic radiative temperature equation, and whatever the albedo and emissivity of the surface ice, the volatile ice is, we get 37 Kelvin. Another time in Pluto's history, though, its pole at perihelion may actually be pointed at the sun. And if the poles are small, if the ice deposits are small enough, the radiative balance will change. That 4 will change to a 2. The temperature changes to 44. You double Pluto's pressure for every Kelvin you increase it. So you could have easily, even with this simple toy model, have gotten Pluto to go from 11 microbars to half a millibar. Okay, so you're almost getting to Mars. And this is for Pluto in its present orbit. It was closer to the sun in the past. It had more insulation, and the pressure was undoubtedly even higher at some point. Although I don't know if what we actually see on Pluto goes back to that time. All of these things, the craters, the tectonics, the atmospheric oscillations, the glaciers, the vapor pressure equilibrium of the main atmosphere are Mars-like. They're more Mars-like than anything else. And I think Pluto is the new Mars. Thank you.
Thank you, Bill. Are there any questions out there? There must be.
Who knows?
How about over here?
Yes, hi, Hal.
Yeah. Yeah, so Pluto is the new Mars, but you know, it's like N2 is so important on Pluto, and that's playing the role of water on Mars, I guess, right? I mean, there's basically, you know, you get the water, H2O on Mars is sort of the equivalent of N2 on Pluto. And where is all that N2 coming from?
No.
Yeah?
N2 is playing, CO2 on Mars plays the role of N2 on Pluto. Okay, so it's the polar caps on Mars that maintain the atmosphere and vapor pressure equilibrium, and the pressure rises up and down throughout the year and across time. Okay.
Okay. For CO2,
So the N, the nitrogen, comes from somewhere. We know that the nitrogen abundance in ice, and let's say in cometary ice as an analog for the ices that built Pluto, is actually a very modest amount. But there's more nitrogen in the organic fraction, and if that gets sufficiently cooked, it may actually somehow get out to the surface. I'll just point out that we have other bodies in the solar system that have a fair bit of nitrogen on them. Titan, as an example, if you actually condense that nitrogen, you get over 100 meters of solid nitrogen on Titan's surface. Okay. So it had to come from somewhere.
Robbie here at UAF.
Hey, Robbie.
I have a question. The large impact that forms this planum, if I understood you right, the efficiency is low, therefore a large portion of the impactor should end up getting distributed on the surface of Pluto, right? And what impact should have a substantial fraction of rock in it, is that right? So this large impact should have dumped a lot of rock on the surface?
Yes.
Okay.
Yes. It's a very astute judgment. And again, here's the transition for ellipticity as a function of cratering efficiency. And like, usually we would say you'd have to be very, very oblique. You'd have to have a very low angle, like 5 degrees, to get an elliptical crater. But that's for lab craters. When you get to something like Sputnik Planum, where you're talking about, you know, an impactor that may be 150 to 300 kilometers wide, it could come in at 45 degrees and still make an elliptical crater. And you're right, a lot of that impactor should be sliding down into this area, which we actually don't see too well because this is right around the terminator. In fact, we see all the wonderful things we see on Pluto, there's stuff at the terminator that is just so tantalizing. It's like, wait, we haven't seen anything like that yet. We have to go back. Somebody in this room has to go back.
Well, some should also go out the sides, right?
Yes.
So,
yeah.
Should that have been preserved over the eons or not?
It may be. It may be off to the side. We see evidence for layering in the terrains to the northwest of Pluto in the craters and in the fracture patterns. Maybe that's the ejecta blanket. Yes, sir.
Yeah, Mike DeSanti, NASA Goddard. Hi. I wondered about the shepherding of the Pluto system by Neptune, right, as it migrated outward. And I think that it's reasonable to assume that a lot of the 3-2 Plutino population had a similar origin. And
yes,
I just wondered how that might affect what we see as the current Pluto system. Or, I mean, could the satellites have been, related to that? I don't know. What's the thinking? I'm just wondering.
I mean, Pluto is cratered by bodies by the Plutino population as well, but the satellites themselves wouldn't be, if you're talking about could they be captured Plutinos. The whole question about small satellites being, I didn't mention this because it's in the paper, the fact that the satellites are in the orbits they have and are bright and icy is inconsistent with sort of capture of any sort of random KBO bodies, which would be substantially
I think that's kind of been brought out also in this session.
Yeah.
But I guess, the whole evolutionary track for the Pluto system as a whole, I find that really interesting.
Yeah. Well, you could actually set it up a different way. You could ask a question: if the Charon forming and small satellite forming impact occurred before the Nix or Nix-like instability, how safe is that system as it has to be evolved through close encounters with, or reasonably close encounters with Neptune or whatever as it moves out? I think that's something that needs to be worked on by people who can.
Okay. Thanks.
Last question.
Yes, sir.
Last question.
Do you expect to be able to constrain the porosity of the smaller moons as maybe a proxy for the impact velocity, whether or not there may be moonlets from the initial impact formation versus exogenous bodies?
I'll actually say yes, and I'll tell you why. Because the masses for Pluto and Charon that go into the density calculation don't come from New Horizons. They don't come from New Horizons gravity. They come from astrometry of the satellite system, which precisely gives the barycenter of the system. So we know the mutual masses of Pluto and Charon. And of course, from Kepler's third law, we get the total mass. The small satellites interact with each other, and the model, the analysis, the astrometric analysis in Brozovic et al., which is published in 2015, gives us masses for the small satellites with sufficiently large error bars that they're not useful now. But I anticipate that refined astrometry from the inbound images that Simon showed, as well as continuing observations from Hubble, will actually at least improve the masses of Nix and Hydra, the larger ones. And since we know how big they are pretty well, I think at this point, we should be able to get their densities. Now, so if that turns out to be 0.6, then you might say, oh yeah, they really are porous. If it turns out to be 1.5, then you don't know. Right, so I'm hopeful on that.
All right.
All right. Thank you very much.
Thank you, Bill.